Get comfortable. Here is what I want you to know before we begin. Right now, somewhere on the outskirts of Paris, in a mansion that even the Nazis did not dare occupy during the occupation of France, behind 3 layers of bulletproof glass and 3 locks whose keys are kept in 3 different countries, there sits a small cylinder made of platinum and iridium, about the height of a chess knight, weighing exactly 1 kilogram, or roughly 2.2 pounds. At least, that was the idea. Because this cylinder, the master kilogram of planet Earth, the standard on which the entire global system of weighing depends, is losing weight. Or more precisely, every time it is compared to its copies, the numbers do not match. The gap is around 50 micrograms per century, half a gram per million years. Sounds like nothing. But when this single object determines every gram of every product, every medication, every chemical element in every laboratory on Earth, even a tiny discrepancy is a crack in the foundation. And here is what is remarkable. This shrinking cylinder is only the latest link in a long chain of errors. Because the meter, the very same meter from which the kilogram was once derived, was also an error. It was calculated by 2 Frenchmen who spent 7 years measuring the distance from Dunkirk to Barcelona in order to figure out the size of the Earth and obtain 1/10,000,000th of the distance from the North Pole to the equator. One of them was named Pierre Méchain. He was a brilliant astronomer, and early in the expedition he made a mistake in his calculations. He realized it, and he hid it. He carried that secret with him to the end of his life, because what was at stake was not just his reputation, but a new system of measurement for all of humanity. The meter, a symbol of pure reason born from the French Revolution, was built on a human deception. And that was not the only case. The Egyptian cubit depended on the length of a specific pharaoh's arm, and when the pharaoh changed, the cubit changed with him. The second was tied to the rotation of the Earth. But the Earth is slowing down, and the seconds stretched along with it. Every measurement we have ever trusted contained a hidden flaw, and every time that flaw was discovered, humanity did not retreat, it leaped forward. Think about this. You live inside a system of 7 base units: the meter, the kilogram, the second, the ampere, the Kelvin, the mole, and the candela. Just 7. From these, absolutely everything else is derived. Newtons, watts, joules, pascals, volts. Every object, every process, every phenomenon in the universe can be described using a combination of these 7 measures. Where did they come from? Who decided that a meter would be a meter and a second would be a second? Why exactly 7 and not 10 or 3? Why are there 60 seconds in a minute instead of 100? And the big question: if every one of these units was born with an error, is it even possible to measure the world precisely? Can you build a perfect ruler, a perfect clock, a perfect scale? Tonight we are going to walk through this entire journey. From cave paintings in France that are 17,000 years old to a vote in Paris in November of 2019, when delegates from around the world raised their hands and forever changed what a kilogram is. We will pass through ancient Egypt, through medieval markets, through the French Revolution, through atomic clocks and lasers. We will meet people who devoted their lives to making measurements just a little more precise, and some who nearly died in the process. No rush. You do not need to remember every detail. If you drift off somewhere in the middle, that is perfectly fine. The story will be here waiting. For now, let us start at the very beginning. At the moment when humans first looked up at the sky and tried to count how long until spring. 17,700 years ago, in the south of France, 4 teenagers and their dog, a dog named Robot, stumbled onto a hole in the ground. A tree ripped up by a storm had exposed the entrance to a cave. The kids came back 4 days later with tools, widened the opening, and climbed inside. What they saw on the walls was one of the greatest archaeological discoveries of the 20th century, the Lascaux Cave. Ceilings and walls covered with images of animals, deer, horses, bulls, painted with such energy that they seemed to race across the stone. These were Cro-Magnons, our direct ancestors, living long before any civilization, long before agriculture, long before the first city. The Lascaux paintings are usually described as art. Beautiful, primal, mysterious. But Dr. Michael Rappengluck, a German researcher who studied the cave for years, noticed something others had overlooked. Among the animals on the walls were strange patterns of dots, not random splotches but repeating groups. 13 dots in a row, then another 13, and another. 13 is 1/4 of a year, if you count by weeks. Each dot represents a 7-day phase of the moon. 7 days for the moon to go from new moon to first quarter, from first quarter to full moon, from full moon to last quarter, from last quarter back to new moon. 4 phases of 7 days, 4 times 13 weeks, and you have a year. But Rappengluck found something else. On the ceiling, 6 dots arranged in a familiar pattern. They looked like the Pleiades constellation, and if Rappengluck is right, those 6 dots were not decoration. They were the starting point of a calendar. When the Pleiades appeared at a specific position in the night sky, it meant the beginning of a new year. The animals on the walls were linked to seasons. A stag with branching antlers, the autumn equinox, rutting season. A pregnant horse, spring. 3/4 of the year, marked on stone. Our ancestors were synchronizing the biological rhythms of animals with the astronomical rhythms of the sky. An incredibly sophisticated system for people who had no writing and no mathematics in the way we understand it. And yet it contained a hidden error. A lunar cycle does not last exactly 28 days. It lasts roughly 29.5. 4 lunar months do not make a full year, but only about 354 days. That is 11 days short of a solar year. Over 3 years, a whole month piles up. The calendar of dots on the wall of Lascaux inevitably drifted, and the people who used it had to adjust it each year by hand, using the stars, the behavior of animals, some set of signs that we can no longer reconstruct. They were measuring time, but their measurement was approximate. And that approximation was enough for survival, but not enough for what would come next. Because roughly 13,000 years later, when people started building cities, growing grain, and trading with one another, approximate knowledge stopped working. Now you needed to know precisely when to plant, precisely when to harvest, precisely how much grain was in a sack, and precisely how many sacks you owed your neighbor. The world demanded measurement. But before we jump to Egypt, it is worth lingering a moment on what happened in between, in those thousands of years between cave paintings and the first civilizations. Because that is when humans made perhaps the most important shift in thinking. They went from observing to measuring. Observing is, the leaves turned yellow, so cold weather is coming. Measuring is, since I marked the 13th dot on the wall, a quarter of the year has passed. Observing is qualitative. Measuring is quantitative. Observing says more or less. Measuring says how much. To measure, you need 3 things. First, a unit, something to compare against. A step, a palm, a grain, a phase of the moon. Second, numbers, a way to count how many units fit into the thing you are measuring. And third, a record, a way to store the result. Dots on a cave wall are a record. Notches on a bone are a record. Knots on a rope are a record. Traces of this shift are scattered across the globe. In South Africa, in Blombos Cave, researchers found pieces of ochre, a red mineral paint, with geometric patterns carved into the surface. They are 77,000 years old. Repeating grids, cross-hatched lines intersecting at angles. Some archaeologists believe this is abstract thinking in its purest form, an attempt to impose a regular, repeating structure on the world. The ruler had not been invented yet, but the idea of the ruler, the idea of equal intervals, was already living somewhere deep in the human mind. In the Congo, the Ashango bone was found, dating to roughly 20,000 years ago. It is a baboon bone with a series of notches arranged in groups. One group contains the sequence 11, 13, 17, 19. Those are prime numbers. Another group 3, 6, 4, 8, 10, 5, 5, 7. Some mathematicians have noted that the sums of notches in different columns produce numbers that are multiples of 10 and 12. Coincidence? Maybe. There is no consensus. But many researchers lean toward the idea that this is evidence of early mathematical calculations, perhaps even a lunar calendar. Then came tally sticks. Wooden sticks with notches for counting livestock, debts, days. 1 notch, 1 unit. 10 notches, 10 units. Measurement in embryo, turning the world into a sequence of identical marks. In England, wooden tally sticks were used by the Treasury to track taxes all the way up to 1826. The stick would be split down the middle lengthwise, one half kept by the taxpayer, the other by the collector. In a dispute, the halves were matched up, and if the notches aligned, the record was considered accurate. The system worked for 700 years. When it was finally abolished, the sticks sat in storage in the basement of Westminster for another 8 years. In October of 1834, officials decided to burn the mountains of old sticks in the palace furnaces. The fire got out of control and destroyed the building. The House of Lords and the House of Commons burned down. And so a measurement system, humble as it was, went out with one of the biggest fires in London's history. These were the first steps. Dots on cave walls, notches on bones and sticks, patterns on ochre. All of them said the same thing. The world can be broken into parts. Those parts can be counted, and the count can be saved. From this simple idea, the entire history of measurement would grow, from the Pharaoh's cubit all the way to the Planck constant. And the first people to answer the call of precision in a serious way were living in the valley of a great river that flooded every year and washed away all the field boundaries. Every year in Egypt, the same thing happened. The Nile flooded, covering the fields for miles around. When the water receded, the land was left fertile. The silt carried by the river was the best fertilizer in the world. But along with the water, the boundaries vanished. The stones marking where one field ended and another began were swept away by the current. And when the water retreated, the arguments started. Where does my field end? Where does yours begin? How much land did I have before the flood? To solve this problem, the Egyptians needed 2 abilities: to measure distances precisely and to build right angles. For distances, they invented the cubit, a unit of length equal to the distance from the elbow to the tip of the middle finger. But not just anyone's arm, the pharaoh's arm. The royal cubit was not an abstraction. It was literally the length of one specific ruler's forearm, about 20 3/4 inches. From this cubit, a measuring rod was made, the cubit stick, the Egyptian equivalent of a ruler. Wooden copies were distributed to surveyors across the country. For right angles, the Egyptians used a knotted rope. The principle is strikingly simple. Take a rope, divide it into 12 equal sections, tie a knot at each division, and connect the ends into a loop. Now stretch the loop into a triangle so that one side has 3 sections, the second has 4, and the third has 5. 3, 4, 5. That is a Pythagorean triple, though Pythagoras would not come along for another 2,000 years. A triangle like that always produces a perfect right angle. Tomb paintings from Egypt show exactly this knotted rope in the hands of surveyors. We even call this triangle the Egyptian triangle. And with a stick and a rope, 4,500 years ago, the Great Pyramid of Khufu was built. 20,000 workers labored for 20 years, laying more than 2 million limestone blocks. The length of each side at the base was 440 cubits, or about 755 feet. The height was 280 cubits, roughly 481 feet. The precision is staggering. The sides of the base differ from one another by less than 4 inches over a total length of 755 feet. That is accuracy of about 0.04%. For a structure built 2,500 years before our era, that is an overwhelming result. But the system only worked as long as there was a strict standard. It is said that every full moon, all the surveyors in Egypt were required to appear before a royal official and check their wooden cubit sticks against the master standard, carved from granite. If a stick did not match, the consequences were severe. Some sources claim the penalty for an inaccurate cubit was death. Even if that is an exaggeration, the very fact that such a punishment was talked about tells you how seriously the Egyptians took the uniformity of their measures. And yet the system was built on a hidden error. The cubit was tied to the body of one person. Pharaohs changed, and with each new ruler, at least in theory, the cubit could change too. On top of that, wood is an unstable material. It dries out, swells from moisture, warps. Even a granite standard could wear down over time. The Egyptian system was brilliant, but it rested on an object, not a principle. And an object, by its nature, cannot last forever. But this was not the only measure the Egyptians gave the world. They did something else, maybe even more important. They divided the day. The Egyptians observed how the shadow of a vertical stone, or a specially carved obelisk, changed throughout the day. At noon, the shadow was shortest, in the morning and evening, longest. They set up a stone, drew lines in the ground, and created a sundial. 12 divisions for daytime, 12 for nighttime, 24 hours in a day. Why 12 and not 10? Why not 5 or 20? The answer probably lies in arithmetic. The number 12 is extraordinarily convenient for division. It can be divided evenly by 2, 3, 4, and 6. Try doing that with 10, and dividing by 3 already gives you a repeating decimal. In a world of trade, where you constantly need to split sacks of grain into equal portions, 12 is the ideal number. There is also a beautiful theory about how people counted on their fingers, not by the fingers themselves, but by the knuckle joints. On 4 fingers of one hand, not counting the thumb, there are 12 joints. You use the thumb of the same hand to touch each joint in turn. 1, 2, 3, up to 12. The other hand counts the dozens, folding 1 finger each time you complete a set of 12. 5 fingers times 12 gives you 60. That is where the 60 minutes in our hour and the 60 seconds in our minute come from. The Sumerians perfected this method, and it outlived their civilization by thousands of years. But sundials, for all their beauty, carried their own error. They did not work at night. They did not work on cloudy days. And most importantly, the length of an hour changed depending on the season. Summer days are longer than winter days, and if you divide daytime into 12 equal parts, a summer hour ends up longer than a winter hour. In Egypt, near the equator, the difference is not that great, about 10 minutes. But at the latitude of, say, London, a winter daylight hour would last only about 30 minutes, while a summer one would stretch to 90. The world lived with these unequal hours for thousands of years. To measure time at night, the Egyptians invented water clocks. A bucket with a small hole in the bottom. Fill it with water, the water drains out, and marks on the inside wall tell you how much time has passed. Simple and brilliant. But here too there was an error. When the bucket is full, the water pressure is higher and it flows out faster. As the bucket empties, the pressure drops and the flow slows down. The clock lied. It ran fast at the beginning and slow toward the end. Centuries would pass before one man in Alexandria solved this problem. His name was Ctesibius. He was the son of a barber, and his invention would literally transform humanity's relationship with time. But before we get to him, we need to understand what was happening with distance measurement beyond Egypt. Because outside the Nile Valley, the world was sinking into a chaos of measurements from which it could not escape for more than 2,000 years. There is one more Egyptian invention worth mentioning, one we use every day without usually thinking about where it came from. It is the concept of scale, the idea that a distance on a map or drawing is proportional to the real distance. The earliest Egyptian drawings, plans of tombs, temples, and irrigation canals were drawn to scale. If on the plan, 2 finger widths separate 2 walls, and in reality the distance is 20 cubits, then the scale is 1 finger width equals 10 cubits. A simple idea, but behind it is a huge conceptual leap. One distance can represent another. Something small can be a model of something large. A map can be a model of territory. This idea lies at the foundation of all modern engineering. Every architectural blueprint, every geographic map, every 3-dimensional computer model is a scaled representation of reality. And it all started with an Egyptian surveyor who one day decided to sketch a plan of a field on papyrus before going out to measure it with a rope. The Egyptians also encountered a problem that would haunt measurement science for millennia: the problem of copying. When you have one granite cubit standard and you need to make 100 wooden copies for 100 surveyors, each copy will differ slightly from the original. Wood is not granite, and a carver is not a machine. And when a year later you need to make copies of the copies, because the originals have worn out, the error accumulates. A copy of a copy of a copy, and after 10 generations your cubit may differ from the original by a whole finger's width. That is why regular calibration was so important. That is why the penalties for an inaccurate cubit were so harsh. The Egyptians intuitively understood what modern metrology calls standard degradation. Over time, without periodic checking and correction, any standard drifts from its original value. Le Grand Quai, slowly losing weight in its Parisian vault, was the same problem, just at a finer level. There is one more unexpected connection between ancient Egyptian measurement and our own time. The Egyptians divided the cubit into 7 palms, and each palm into 4 fingers. That gives 28 fingers in 1 cubit. 28 is 4 times 7. 4 weeks of 7 days, 1 lunar month, 12 and 7 again, another link between distance and time, between space and rhythm. The ancient world did not draw such a sharp line between these things. For the Egyptians, the same harmony ran through sky, earth, and the human body alike. A measure of length and a measure of time were reflections of one and the same cosmic order. We, modern people, know this harmony is a projection of the human mind, not a property of the universe. There is no physical reason why a cubit should contain 28 fingers and a lunar month 28 days. Coincidence, not law. But the beauty of the coincidence remains, and it was precisely that beauty that drove our ancestors when they tried to build an orderly, consistent system of measures. They were looking for pattern in chaos, and they found it. Sometimes correctly, sometimes not, but always with a persistence that deserves respect. We mentioned 12 and 60, the numbers on which our entire system of time is built. But this topic deserves a longer pause, because the story of these numbers is one of the most remarkable in world culture. It begins long before Egypt, in Mesopotamia, in the fertile delta of the Tigris and Euphrates, where around 3,000 years before our era, the Sumerian civilization flourished. The Sumerians are a people about whom we know a surprisingly large amount, considering how long ago they lived. They invented one of the first writing systems, cuneiform, pressing reed styluses into clay tablets. They built ziggurats, stepped temples that would later inspire the biblical story of the Tower of Babel. They created the first codes of law, and they counted not in tens, but in 60s. Why? There are several theories, and none of them has been definitively proven. One of the most elegant involves fingers, but not the kind of finger counting we are used to. We count using 10 fingers. The Sumerians, it seems, counted using knuckle joints. On 4 fingers of one hand, leaving out the thumb, there are 12 joints. You touch each joint with the thumb of the same hand. 1, 2, 3, up to 12. When you have gone through all 12, you fold one finger on the other hand and start over. 5 fingers times 12 gives 60. A simple, elegant system that lets you count to 60 with 2 hands and nothing else. Another theory is purely arithmetic. 60 is a record-breakingly convenient number for division. It can be divided evenly by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. 12 divisors, more than any other number of similar size. For traders who constantly needed to split goods into equal portions, this was an incredibly valuable property. Try dividing 100 grains into 3 equal piles, and you will have to start cutting grain. 60 grains into 3, 20 in each pile, no problem at all. The Sumerian base 60 system did not disappear with the Sumerians. It was inherited by the Babylonians, then the Assyrians, then the Persians, then the Greeks. The Greek mathematician Ptolemy, who lived in the 2nd century of our era in Alexandria, used the base 60 system for astronomical calculations. He divided the circle into 360 degrees, 6 times 60. Each degree into 60 parts that he called partes minutae primae, first small parts, or minutes, and each minute into 60 partes minutae secundae, second small parts, or seconds. That is where the words minute and second come from. Minute literally means small part. Second means second small part. We are so used to these words that we never think about their origin. But every time you say 30 seconds or 5 minutes, you are pronouncing Latin words describing a division conceived by a Greek who used numbers invented by the Sumerians 4,000 years earlier. And these numbers, 12 and 60, turned out to be incredibly resilient. They survived dozens of civilizations. They withstood the metric system, which tried to replace them with tens. The French revolutionaries who created the meter and the kilogram also tried to introduce decimal time. 10 hours in a day, 100 minutes in an hour, 100 seconds in a minute. Special clocks were manufactured with 2 dials, 1 decimal and 1 traditional. The hour hand on the decimal clock made 1 revolution per day instead of 2. The idea did not stick. People simply could not get used to it. Centuries of habit proved stronger than revolutionary zeal. Decimal time was officially in use for less than 2 years, from the autumn of 1793 to the spring of 1795, and was quietly abolished. Napoleon, when he came to power, did not even try to revive it. He understood that there are limits to what you can impose on a population by force. The decimal calendar lasted a bit longer, and, it must be said, had its own beauty. It had 12 months of 30 days each, totaling 360, with the remaining 5 days, 6 in a leap year, treated as holidays that belonged to no month. Each month began on the first day of a 10-day week called a decade. Every day of the year had its own unique name tied to nature: Lavender Day, Wheat Day, Dog Day, Grapevine Day. A poetic, rational, elegant calendar. It was in effect for 12 years, from 1793 to 1805, after which Napoleon brought back the Gregorian calendar, and the French 60-second minute survived its only serious threat. 12 hours on the clock face, 60 minutes in an hour, 60 seconds in a minute, 360 degrees in a circle. These numbers are fragments of a world that vanished 5,000 years ago, yet whose breath we feel every time we look at a clock. Imagine you are a merchant in medieval Europe. You buy cloth in one city to sell in another. But in Lyon the foot is one length, and in Marseille it is another. A pound of silver in Genoa is not the same as a pound of silver in Venice. And even if you memorize all the local measures along one trade route, next year some duke might change them because he wants to, because he can, because his arm is longer or shorter than the arm of the previous ruler. This is not an exaggeration. In the 12th century in England, the yard was defined as the distance from the tip of the king's nose to the end of his outstretched thumb. Henry II defined the yard as the length of his arm. Elizabeth I, apparently unwilling to be outdone by her male predecessors, added a few inches. Every new monarch, a new yard. Every new yard, a recalculation of every existing measure. But at least in England there was one crown and, in theory, one standard. In France, by the end of the 18th century, the situation was incomparably worse. Across a single country, there were more than 250,000 different units of measurement. 250,000. Several thousand of them were just for length. Measures changed not just from city to city, but from market to market, from guild to guild. A tailor's foot could differ from a carpenter's foot in the same town. The consequences were entirely practical. Trade was painfully slow because every transaction required conversion. Fraud thrived, since it was easy to cheat a buyer who did not know the local measures. Navigation was dangerous because sea charts drawn in one system did not line up with charts from another. An architect who drew a building plan in Paris could not be sure that builders in Lyon would reproduce it accurately because their inch might turn out to be a different inch. Attempts to tame the chaos came again and again. The famous Magna Carta, one of the most important legal documents in history, contained a clause requiring a single measure for wine, ale, and grain throughout the kingdom. It sounded wonderful on parchment. In practice, it was nearly impossible to enforce. Inspections were held regularly, with officials visiting markets and checking merchants' scales and measures against standards. Those whose measures did not match were punished. The Babylonian Code of Hammurabi, written as far back as 1770 BC, prescribed the death penalty for a tavern keeper who used false measures. In 18th century England, bankers caught cheating with scales were put in the pillory, and brewers were tied to a chair and dunked in water. Scales are a story unto themselves. Ever since the simplest beam balance was invented in Mesopotamia around the 3rd millennium BC, scales became a symbol not just of commerce, but of justice. In ancient Egypt, the god Anubis weighed the heart of the dead on a scale, comparing it with the feather of Maat, goddess of truth. If the heart was heavier than the feather, a monster devoured the soul. Scales appear in Dutch master paintings, on courthouse facades, in the hand of the statue of Lady Justice. As the Bible says, by number, measure, and weight, God created all things. But even the best scales could not solve the main problem, the lack of a single standard for what exactly sat on the other pan. The first universal weights were grains. A barley grain, small, relatively uniform in weight, available to anyone. You could walk into any market in any Mesopotamian city, and if the merchant said 500 grains of silver, you could count out 500 barley grains and check. Over time, grains were replaced by standardized weights made of stone and metal, but the system itself stayed tied to the grain. The English word grain is still used as a unit of mass in certain contexts, like measuring gunpowder charges and bullets. The problem is that grains, of course, are similar to one another but not identical. One grain is a bit heavier, another a bit lighter. With 5 grains, the difference is invisible. With 5,000, it is noticeable. And in the Roman Empire, where millions of tons of goods moved every day, even a small error multiplied by scale turned into an enormous loss, or an enormous profit for those who knew how to exploit it. And this is where we arrive at a key moment. The reason this tangled history of measures is not just an old curiosity, but a direct line to our present. All these measurements, from dots on the wall of Lascaux to barley grains, from the pharaoh's cubit to the king's yard, were tied to something concrete, physical, and imperfect. To an arm, to a grain, to a stone, to the body of one person. To break free from this chaos, a radical idea was needed. Tie measurements not to a person, not to an object, but to something larger than any person and any object. Something that cannot wear out or die or be counterfeited. That idea appeared at the most turbulent moment in European history, when France rose up against its kings and, along with the monarchy, decided to tear the old world of measurement down to the ground. And for this, two men were given an assignment that sounds almost like madness. Measure the size of the earth. Let us linger a bit more on the chaos of medieval measures, because its scale is hard to overstate, and it is critical for understanding why the metric system sparked such excitement among the revolutionaries. In medieval France, every feudal lord had the right to set his own measures within his territory. This was not just anarchy, it was a tool of control. If you are a lord and you decide that your boisseau, a grain measure, is 10% larger than the boisseau of your neighboring lord, then the peasants paying you tribute have to give more grain for the same amount. And when you sell that grain at the neighboring lord's market, using his smaller boisseau, you get more measures for the same volume. The difference in measures is a hidden tax. Everyone knew it, and everyone was powerless to change it, because the right to define a measure belonged to whoever owned the land. The philosopher Condorcet, one of the architects of the French Revolution, wrote that the inequality of measures was one of the most tyrannical features of the old regime. The measure, he said, should belong to the people, not to the king. That is why the metric system was so tightly linked to revolutionary ideals. One measure, one nation. Equal measure, equal citizens. The meter was not just a unit of length, it was a political statement. One of the most telling documents of that era is the so-called cahiers de doléances, or notebooks of grievances. Lists of complaints drawn up by residents of every city and village in France before the convening of the Estates General in 1789. Historians have calculated that a complaint about the chaos of weights and measures appears in nearly every third notebook. People were fed up. They wanted one simple thing, for a pound in Lyon to weigh the same as a pound in Marseille, for a yard of cloth in Rouen to be the same length as a yard of cloth in Bordeaux, for trade without having to recalculate every measure from scratch. When the Academy of Sciences proposed the metric system, it poured into it all the passion of the Enlightenment. The system was to be rational, based on the decimal system, rather than fickle 12s and 60s. It was to be universal, tied to nature rather than to the body of a king. And it was to be reproducible, so that anyone with instruments could verify whether a measure was correct. In 1792, Joseph Louis Lagrange, the greatest mathematician of the era, gave a speech before the Academy defending the decimal system. He was challenged. Would it not be better to use a base 12 system, since 12 has more divisors than 10? Lagrange's answer was brilliant. Yes, if we were inventing a counting system from scratch, 12 would be the better base. But we are not inventing from scratch. We live in a world where everyone already counts in tens, and it is pointless to replace one system with another just for the sake of mathematical elegance. 10 fingers. Decimal system. The meter, divided into 10 decimeters, 100 centimeters, 1,000 millimeters. Simple, logical, democratic. That decision to base the metric system on tens shaped its future. Decimal fractions are easy to add, multiply, and divide. Converting between units is just moving the decimal point. 1 kilometer is 1,000 meters. 1 kilogram is 1,000 grams. 1 liter is 1,000 milliliters. No 12 inches in a foot, 3 feet in a yard, 1,760 yards in a mile. The metric system did not just standardize measures, it simplified the very act of thinking about measures. And although the transition was painful, French peasants continued using the old measures for decades, and Napoleon, as we already know, even officially allowed their parallel use. The logic of the decimal system eventually won. By the start of the 21st century, the metric system had become the standard in almost the entire world. Out of more than 190 countries, only 3, the United States, Myanmar, and Liberia, still have not adopted it as their sole system. Among all the instruments of measurement, scales hold a special place. A ruler measures length, a clock measures time, and scales. Scales measure justice. At least, that is what our ancestors believed. Beam balances were invented in Mesopotamia, roughly 3,000 years before our era. The design is simple to the point of genius. A horizontal bar suspended at its center, with a pan on each end. Place the goods on one pan, place weights on the other. When the bar levels out, the goods weigh the same as the weights. The lever principle in its purest form. Archimedes would say, "Give me a fulcrum, and I will weigh the world." The first weights, as we already know, were grains, barley or wheat. Grain is amazingly convenient for this purpose. It is small, relatively uniform in weight, available to everyone. A caravan could carry a sack of grains and use them as universal weights at any market from Babylon to India. Over time, grains were replaced by standardized weights made of stone, ceramic, and metal. But the unit of mass in many systems remained tied to the grain. The English grain is about 1/437th of an ounce. It is still used in some specialized fields, like weighing powder charges and bullets. Scales quickly became a symbol of something larger than trade. In ancient Egypt, the image of scales appears in the Book of the Dead, one of the most important religious texts. The god Anubis leads the soul of the dead to the scales. On one pan is placed the heart of the deceased, on the other the feather of Ma'at, goddess of truth and order. If the heart is lighter than or equal to the feather, the soul gains eternal life. If heavier, it means the heart is burdened with sin, and the monster Amit devours it. Scales as an instrument of divine judgment, measurement as an act of absolute justice. This metaphor proved incredibly durable. The Greek goddess Themis holds scales in her hands. The Roman Justitia does too. When medieval European cities built courthouses, they placed a figure with scales above the entrance. When laws were written, they included paragraphs about the accuracy of weights and measures, because trade was the foundation of the urban economy, and cheating with scales was the most common and most destructive form of fraud. Punishments for false scales were harsh across all cultures. The Code of Hammurabi prescribed the death penalty for a tavern keeper using fraudulent measures. In medieval England, a dishonest trader could be tied to the pillory with false weights hung around his neck. Brewers who watered down their ale and sold it by weight were strapped to a special chair and dunked in a river, a so-called ducking stool. You can imagine that was not the most pleasant punishment, especially in winter. But the most interesting thing is how scales changed the very concept of value. Before scales existed, exchange was direct. I give you a basket of fish, you give me a sack of grain. But how much fish is one sack of grain worth? Without a single system of measurement, every deal is a negotiation, an argument, a haggle. With scales came the ability to reduce everything to a single number: weight. Fish is worth so many grains of silver. Grain is worth so many grains of silver. And from that, you can calculate the exchange rate of fish to grain, without bargaining every time. This changed everything. It made it possible to build economies based not on direct barter, but on monetary systems. Money is, at bottom, a standardized measure of value. And a standardized measure of value is impossible without a standardized weight. Coins were minted at a specific weight, and their purchasing power depended on how much silver or gold was in them. If a coin weighed less than it should, someone had clipped the edges or mixed in a cheaper metal. By the time of the Roman Empire, millions of tons of goods moved daily across the entire Mediterranean world. Grain from Egypt, olive oil from Spain, wine from Gaul, silk from the Far East. All of it weighed, valued, exchanged, and at the base of this colossal trade system sat scales. Two pieces of wood hung from a center point, with pans on each end. A 5,000-year-old principle. The same principle later used by the Watt balance at the National Institute of Standards and Technology in the 21st century. Except that instead of grains on the second pan, there was electromagnetic force. You could say that scales are the longest-lived instrument in human history. 5,000 years ago they looked one way. Today, inside electronic scales sits a strain gauge, a tiny piece of wire whose electrical resistance changes when it is deformed. When you place something on the platform, the wire compresses slightly. The resistance changes, the electrical current changes, and a microchip converts that change into a number on the display. The principle is completely different, but the goal is the same. Find out how much something weighs. Strain gauges are used everywhere. Under railroad tracks to weigh coal cars on the move at over 40 miles per hour, each car in a fraction of a second. At highway weigh stations to check how loaded trucks are. In supermarkets, every self-checkout register uses strain gauges. One researcher demonstrated the precision of this technology by simply stepping onto railroad scales with his feet. They showed his weight, about 186 pounds, with the same ease with which, a second earlier, they had weighed a 200,000-pound rail car. We can weigh anything, from 200,000-pound rail cars to individual cells. In Scott Manalis's lab at MIT, cells pass through a microscopic channel inside a silicon chip. When a cell passes through the channel's vibration frequency changes, the same way a guitar string changes pitch when you press a finger on it. From the frequency change, Manalis determines the mass of the cell. A single white blood cell weighs about 10 picograms, 10 trillionths of a gram, roughly 350 trillionths of an ounce. And the measurement precision is 10,000 times finer than that, in femtograms, quadrillionths of a gram. Think about that. From a barley grain to quadrillionths of a gram. 5,000 years of progress, and the principle remains the same. Compare an unknown mass against something known. What changes is only the scale and the nature of the known thing you are comparing against. It used to be a grain, then a stone, then a platinum cylinder. Now, it is the Planck constant. On March 26, 1791, the French Academy of Sciences made a decision that was meant to change the world. Enough of tying measurements to the body of a king. Enough of adjusting to the vanity of monarchs. The new unit of length was to be based on something permanent, unchanging, and belonging not to one nation, but to all of humanity. They chose the Earth. The new unit would be called the meter, from the Greek metron, meaning measure. The meter was to be 1/10,000,000th of the distance from the North Pole to the equator, measured along the meridian passing through Paris. The choice was both scientific and political. The Academy understood that a French unit of measurement would never be accepted by other countries if it looked like something purely French. But if the unit was based on the planet itself, who could object? This system is for all people, for all time, the revolutionary government declared. There was one small problem. Nobody knew exactly what the distance from the North Pole to the equator was. To find out, They needed to carry out the most ambitious and complex geodetic expedition in history. The assignment went to two men, Jean-Baptiste Delambre and Pierre Michin. The plan was this. Delambre would work from Dunkirk in the north, Michin from Barcelona in the south. They would move toward each other, meeting at Rodez in southern France. The method was triangulation. You pick two visible points on the horizon, a bell tower, a hilltop, a tower, and measure the angle between them with a special instrument. Then you move to one of those points and repeat the procedure. Knowing one precise distance and a series of angles, you can use trigonometry to calculate all the other distances. The instrument they used was called a repeating circle. It was a device with two telescopes that could measure angles with remarkable precision. The instrument was so well made that it worked just as reliably as the day it was manufactured, and it has survived to this day. The principle was elegant. You only needed one accurately measured distance, a baseline, and then you could triangulate for hundreds of miles without measuring each one directly. One line segment and a chain of triangles stretching from the North Sea to the Mediterranean. Delambre began his journey in 1793 from the bell tower in Dunkirk. Picture him standing at the top with this complex optical instrument peering at the horizon, trying to find two distant points to start his first triangle. Before him lay 7 years on the road. He did not know that yet. He thought he could finish in a year or two. The expedition took place during the height of the Revolution, and then the Terror. Delambre was arrested several times. He would climb bell towers and church steeples carrying strange equipment, and the local militia would take him for a spy. Once, a drunk militiaman cut short his explanations. "There is no more academy. We are all equal now. You are coming with us." Delambre had to prove again and again that he was not an enemy of the Republic, but a scientist measuring the earth for the good of the nation. Sometimes it worked, sometimes it did not. Michin worked on the southern leg, from Barcelona northward. He was a different person by temperament, more withdrawn, more anxious, more obsessed with precision. Delambre was an optimist who could weather a setback and move on. Michin was a perfectionist for whom every inaccuracy was a personal defeat. That quality would become his curse. Michin's task looked simpler. His section was shorter, and part of his route passed through Spain, which had no revolution. But Michin ran into trouble immediately. He needed to make observations from the observatory in Barcelona to determine the city's latitude, a critical step for calculating the total distance. And here, right at the start, something went wrong. Michin conducted a series of observations, calculated the latitude of Barcelona, and recorded the results. Then, months later, he conducted repeat observations from a different location within the city, from the other end, to double-check. And he got a different number. The difference was small, about 3 arc-seconds. For an ordinary person, that is nothing. For an astronomer whose job was to measure a quarter of the Earth's circumference and derive from it a universal unit of length, it was a disaster. 3 arc-seconds of latitude at Barcelona meant a difference of roughly 650 feet on the ground. That sounds small. But the entire idea behind the meter was that it had to be precise, not approximate, not roughly this much. Precise. 1/10,000,000th of the distance from the pole to the equator, and if the initial data contained an error, the whole calculation would shift. Michin could have reported the discrepancy honestly. He could have sent the data to the academy and said, "Here are 2 numbers, they do not match, we need to figure out why." But he did not do that. He could not do that. Or at least, that is how it felt to him. Why? Ken Alder, who wrote a book about this story called The Measure of All Things, believes there were several reasons. First, Michin was painfully perfectionistic. An error was not a technical issue for him, but a moral one. He felt that he had let down not just the project, but the very idea. The idea that the world can be measured precisely, that the human mind can grasp nature and express it as a number. Second, the context. France was in chaos. The academy was being shut down and reopened. Scientists were being imprisoned. Lavoisier, France's greatest chemist, who had begun work on the kilogram, was sent to the guillotine in 1794. Mechain may have feared that admitting the error would put the entire project at risk, and with it, his life. And he did what people do when they are scared and overwhelmed. He buried the problem. He chose one of the two values, the one that looked more plausible, and presented it as final. The other value he wrote in his notebooks, but he told no one. 7 years. That is how long the expedition lasted. 7 years of climbing towers and descending into valleys, 7 years of recalculations and cross-checks, 7 years living on the roads of a France torn by war and revolution. Delambre completed his northern section. Mechain completed his southern one. They met. The data were combined. And based on these data, including Mechain's hidden error, the size of the Earth was calculated, and from it, the length of the meter was derived. In 1799, a platinum bar was ceremonially placed in the National Archives of France in Paris, intended to embody 1/10,000,000th of a quarter of the Earth's meridian. The meter. The first unit of length not tied to the body of a king, but derived from the size of the planet itself. It still lies there today. Beautiful not so much as an object, but as an idea. That piece of platinum represents a shift in thinking. For the first time, a measurement was based on something that seemed eternal and unchanging. Seemed. Because the meter born from this expedition contained an error. Not a huge one, about 8/1000ths of an inch per meter, not much, but enough that it did not correspond exactly to what it was supposed to be. Mechain knew about this, and this knowledge ate at him from the inside. After the expedition was completed, he asked permission to return to Spain and repeat the observations, to recheck, to correct, to perfect. The Academy agreed. In 1803, Mechain headed south. But before he could complete the repeat observations, he fell ill with malaria. And on September 20th, 1803, Pierre Mechain died in Castellón, on the Mediterranean coast of Spain. He was 54 years old. Only after his death, when Delambre gained access to Mechain's notebooks, did the truth begin to emerge. Delambre found both sets of Barcelona data. He saw the discrepancy. He understood what had happened. And he made a decision that was, in a way, the mirror image of Mechain's. He did not make a scandal. Delambre included both series of data in his final report, published in 1806 and 1810, presenting them simply as two sets of observations, without emphasizing the contradiction. Mechain's error, in the end, did not affect the further history of the meter, because by that point, the meter had taken on a life of its own. The platinum bar in the Paris archive became the meter, regardless of whether it precisely matched 1/10,000,000th of the meridian. The world adapted not to an ideal length, but to this specific bar. The error became the standard. Napoleon, who by then was ruling France, took a pragmatic view of the meter. He understood its value for administration and trade, but felt no sentimental attachment to it. His famous remark, "Conquests come and go, but this will endure," was most likely said about the metric system. And he was right. Napoleon conquered nearly all of Europe, and along with his armies he spread meters and kilograms. But here is what is interesting. The countries that successfully resisted Napoleon, England and Russia, took far longer to adopt the metric system. England defeated Napoleon at sea and on land and kept its feet, inches and miles well into the 1970s. Russia repelled Napoleon and switched to meters only after the revolution of 1917, more than a century later. And as for America, the ship carrying the new measurement standards reportedly never arrived. A storm blew it into the Caribbean, where pirates attacked it. So the next time you see a TV screen size listed in inches, you can thank that storm and those Caribbean pirates. The meter conquered the world, slowly, with resistance, but irreversibly. By 1875, 17 countries signed the Meter Convention and established the International Bureau of Weights and Measures, the BIPM. That was the moment when measurement became truly global. 1 meter for all, 1 kilogram for all. But alongside the meter all this time lived its younger brother, the kilogram. And the kilogram story turned out to be even more tangled, even more dramatic. Because while the meter was merely slightly inaccurate, something worse happened to the kilogram. It started changing. Slowly, undetectably, but unstoppably. The master kilogram of the planet was losing weight. We left Mechain with his secret, but the expedition's story deserves more time. Because the 7 years that Delambre and Mechain spent on the road were not just a technical exercise. This was one of the most incredible scientific odysseys in history, and it unfolded against the backdrop of a world that was literally falling apart. When Delambre began his work in the spring of 1792, France was still a constitutional monarchy. Louis XVI was still sitting in the Tuileries. Within months, the monarchy would fall, the king would be arrested, and by January of 1793, he would be executed by guillotine. The terror that followed would claim thousands of lives. The Academy of Sciences, which had sent 2 scientists to measure the Earth, would be shut down by the revolutionary government because academies were associated with the old regime. Scientists would begin to be persecuted as potential enemies of the revolution. Delambre was on the road when all of this was happening. Picture his situation. You are standing on top of a bell tower in a small French town, aiming your instrument at a distant church on the horizon. Below you, a crowd of revolutionary-minded townspeople who do not understand what you are doing and suspect the worst. You are carrying papers from an organization that officially no longer exists. Your mission was authorized by a government that may have already been overthrown, but you do not know for certain because news takes weeks to reach the provinces. Delambre was arrested at least 6 times. Each time he managed to get out, sometimes with the right documents, sometimes with eloquence, sometimes through sheer luck. Once he was detained at a city gate because his repeating circle, a complex astronomical instrument, had royal fleur-de-lis engraved on it. During the Terror, that symbol alone was enough to send you to the guillotine. Delambre explained that the fleur-de-lis was part of the factory marking, and that their presence on the instrument did not make him a royalist, just as the name on an axe does not make a woodcutter a supporter of whoever's name is on the axe. A risky argument, but it worked. Mechain, on the southern leg, encountered problems of a different kind. Part of his route passed through Spain, and France soon went to war with Spain. Mechain found himself in a country that was at war with his homeland. He was barred from leaving. He was stuck in Barcelona for several months, and it was during this time that he conducted the repeat observations that produced the discrepancy. He spent those long nights in the observatory, staring at the stars and realizing that the numbers did not match. And he could not get back to France because of the war. When it was finally possible to cross the border, Mechain set out for home. But along the way he was seriously injured. He fell off a mule and hurt his arm and ribs. He spent several weeks in bed, unable to work. And all that time, his secret, the discrepancy in the Barcelona data, lived inside him like a splinter that could not be pulled out. Meanwhile, the expedition acquired an additional task. The Academy, during the intervals when it was alternately shut down and reopened, decided that in addition to measuring the meridian, 2 baselines needed to be measured. Straight stretches of terrain whose length would be determined directly, not through triangulation. These baselines were the anchors of the entire system. If you got the baseline length wrong, all subsequent calculations would shift. Measuring a baseline was grueling work. You had to lay special rulers, platinum rods about 13 feet long each, end to end along the ground, one rod after another, measuring the distance. Each rod had to be perfectly leveled, compensated for thermal expansion, corrected for the curvature of the Earth's surface. Measuring a single baseline about 6 miles long took weeks. Delambre performed this measurement near Melun, south of Paris, in 1798. He was assisted by a small team that included the young mathematician Jean-Baptiste Biot, who would later become a famous physicist in his own right. The work was exhausting, crawling along the ground, laying down rods, checking their horizontality, recording the temperature because platinum expands when heated, all under a blazing sun, in conditions where armed patrols roamed the countryside and any passerby could turn out to be an informant. There is one episode that vividly illustrates the absurdity of the situation. Delambre was working at the top of a church tower when a crowd gathered below, demanding that he remove the cross from the steeple, a symbol of religion that the revolutionaries considered a relic of the old regime. Delambre came down and explained that the cross served as his geodetic reference point, the target at which he aimed his instrument from another city. If the cross was removed, he would have to build another tower, which would take weeks. The crowd reluctantly agreed to leave the cross in place. Science saved a church cross, at least for a while. The expedition went on. Delambre moved south, Méchain moved north. They were supposed to meet in Carcassonne, in southern France. The moment of meeting, when 2 datasets, one from the north and one from the south, would finally be combined, was supposed to be a triumph. All those years, all those towers and bell steeples, all the arrests and illnesses, everything had been leading to a single number. The distance from Dunkirk to Barcelona. From that distance, knowing the latitudes of both points, they could calculate the length of a quarter of the meridian, and dividing by 10 million, arrive at the meter. When the data were finally combined in 1798, an international commission convened. Representatives arrived from Denmark, Holland, Spain, Switzerland, and several Italian states. England refused to participate, partly for political reasons, partly because it did not want to adopt a French unit. The Commission reviewed the calculations, certified them as correct, and officially established the length of the meter. Méchain sat through those sessions, knowing that his data contained a discrepancy he had not reported. Ken Alder, who reconstructed this story from archival documents, describes Méchain during this period as a man crushed by the weight of his own secret. He could not eat, he slept poorly, he became increasingly withdrawn. Colleagues noticed the changes but attributed them to exhaustion after the 7-year expedition. The truth is that Méchain's error, 3 arc-seconds, introduced a discrepancy of roughly 650 feet in the determination of the length of a quarter of the meridian. Translated into the meter itself, it meant an error of about 0.008 of an inch, making the meter slightly shorter than it should have been. Not a catastrophe, but not zero either. The paradox is that even if Méchain had not made his error, the meter still would not have been perfectly accurate. Because the Earth is not a perfect sphere. It is slightly flattened at the poles and slightly bulging at the equator. Moreover, its shape is irregular, with dips and bumps caused by uneven distribution of mass in the crust and mantle. The meridian passing through Paris has a slightly different curvature than the one passing through London or Berlin. 1/10,000,000th of 1/4 of one meridian does not equal 1/10,000,000th of 1/4 of another. The idea of tying the meter to the size of the Earth was conceptually beautiful, but physically, the Earth is an imperfect standard. All of this became clear much later. At the time the meter was created, these subtleties were unknown or considered negligible. And the main lesson here is not that Méchain made a mistake, but that the task itself was set up in a way that made a perfectly accurate answer impossible. The Earth is not suited for the role of an ideal standard, just as the pharaoh's arm was not suited for that role 2,000 years earlier. The Earth is simply a better standard than an arm, but still an imperfect one. And this realization that physical objects, whether an arm, a rod, or a planet, cannot be ideal standards, is the root of everything that came next. The entire subsequent history of metrology could be given one title: The Escape from Objects to Laws. The story of the kilogram begins beautifully, perhaps more beautifully than the story of any other unit, because the kilogram was conceived as a bridge between the meter and nature. The idea was simple. If you have a meter, you can build a cube with sides 1/10 of a meter long, a decimeter. Fill that cube with pure water, and the mass of the water inside is 1 kilogram. Meter, liter, kilogram, all linked through water. Anyone with a ruler and access to clean water could reproduce a kilogram at home. Elegant, democratic, revolutionary. The assignment, turning this idea into a real standard, went to Antoine-Laurent Lavoisier, the greatest chemist of his time. By day, Lavoisier worked as a tax collector. That was how he earned money. By night, he did chemistry. That was how he changed the world. Lavoisier was the one who disproved the phlogiston theory, proved the role of oxygen in combustion, and wrote the first modern chemistry textbook. His intellect, rigor, and experimental precision made him the ideal person to define the kilogram. But turning a cubic decimeter of water into a precise unit of mass turned out to be unexpectedly difficult. Water is a tricky substance. Take 2 perfectly identical cubes. Fill both with water, one with cold, the other with hot. Cold water is denser than hot water, so the cube with cold water weighs more. At about 39 degrees Fahrenheit, water is at its densest, roughly 2.2 pounds per cubic decimeter. At 194 degrees Fahrenheit, only about 2.13. A difference of over an ounce or 3%, which for a base unit of mass is unacceptable. Temperature is just one variable. There are also impurities. Even the purest natural water contains dissolved salts, gases, microscopic particles. There is atmospheric pressure. Water behaves slightly differently under different pressures. There is altitude. Gravity at the top of a mountain is weaker than at the base, and the same volume of water weighs slightly differently. Lavoisier was close to solving all these problems. His experimental technique was possibly the best in the world. But on May 8, 1794, his career ended, along with his life. The revolution that gave birth to the metric system devoured one of its creators. Lavoisier was executed by guillotine as a tax collector. His scientific achievements were not a mitigating factor. The mathematician Lagrange said after the execution, "It took a second to cut off that head. It will take a century to grow another one like it." Others picked up the work, Louis Lefebvre-Ginot and Giovanni Fabroni. For 4 years they refined the method of weighing distilled water with controlled temperature and purity. And finally, on June 22, 1799, they presented the nation with a prototype kilogram, a platinum cylinder given the name Kilogram of the Archives. It was placed alongside the meter standard in the French National Archives. But pure platinum, for all its resistance to air and water, is a soft metal. It scratches easily, and microscopic pieces chip off without much effort. Hundreds of copies distributed to cities and towns across France gradually wore down. Every scratch meant lost micrograms. Over decades, a noticeable difference accumulated. A new, harder standard was needed. In 1875, when 17 countries signed the Meter Convention, it was decided to create a new international kilogram from an alloy of platinum and iridium. Iridium gave the alloy the hardness that pure platinum lacked. The order went to the London firm Johnson Matthey, the world leader in processing precious metals, headed by George Matthey, the best platinum caster on the planet. French pride demanded that the casting take place not in London but in Paris, at the Conservatory of Arts and Trades. This turned into a disaster. The platinum was contaminated with iron, and the entire batch, about 550 pounds of precious alloy, was unusable. A massive blow to the budget and to French self-esteem. On the second attempt, this time in London, Matthey finally cast the perfect cylinder. Height, about 1.5 inches. Diameter, about 1.5 inches. A ratio that minimizes surface area for a given volume to reduce contact with air and therefore contamination. The cylinder was christened Le Grand K, the Big K. It was placed in the basement of the International Bureau of Weights and Measures, BIPM, in Sèvres, on the outskirts of Paris, in a building granted the status of international territory. From that moment on, 1 kilogram was whatever Le Grand K weighed. Not a cubic decimeter of water, not some abstract quantity. A specific object lying in a specific basement in a specific city. 40 copies were sent out to the countries that had signed the Meter Convention. Each country periodically shipped its copy to Paris for comparison with the original. And then, roughly 100 years later, something troubling was discovered. During a comparison at the end of the 20th century, it turned out that the copies were gaining weight, or Le Grand K was losing it. The difference was tiny, about 50 micrograms per century, roughly the weight of a single grain of sand. But the trend was consistent. With each comparison, the gap grew, and it was impossible to determine who was at fault, the original or the copies. Le Grand K was compared to the copies, and the copies to Le Grand K. There was no external point of reference. The kilogram was defined as this specific object, and if the object changed, the kilogram changed with it. The entire global system of mass rested on a foundation that was quietly crumbling. By the way, as you lie here listening, your phone on the nightstand uses the kilogram every time the accelerometer inside it figures out which way is down. That accelerometer works with units of force, and units of force are defined through the kilogram. Invisible, unnoticed, but the link is there. And if the kilogram drifted far enough, so would your phone's understanding of gravity. You might ask, so what? A grain of sand over 100 years. Who cares? Everyone who works at the edge of precision cares, and in the modern world, that means millions of people and organizations. Pharmaceuticals, where a drug dose must be accurate to the microgram. The semiconductor industry, where layer thickness is measured in nanometers. Particle physics, where the mass of a proton is known to 12 decimal places. All these fields depend on the kilogram, and all of them feel it when the kilogram starts to drift. But solving the kilogram problem ran into a deep conceptual question. What do you tie mass to, if not to an object? By this time, the meter had already been redefined. In 1983, it was tied to the speed of light. The second had been tied to the vibrations of a cesium atom even earlier. These units no longer depended on specific artifacts. They were based on fundamental properties of the universe, properties that are the same at any point in space and time. The same thing needed to be done with the kilogram, but how? More on that later. Because before we get to the redefinition of the kilogram, which would not happen until 2019, we need to talk about what happened with time, with the second, with clocks. Because the story of the second is what showed humanity how to tie measurements to atoms, and that method would eventually save the kilogram too. And the story of the second begins with a man who watched water dripping in his father's barbershop. Before we move on to the story of the second, it is worth making an important detour. Because there is a subtlety connected to the kilogram that often slips past unnoticed, but which cannot be skipped in an honest account of measurement. It is the difference between weight and mass. In everyday speech, we use these words as synonyms. I weigh 154 pounds. But strictly speaking, the kilogram is a unit of mass, not weight. Mass is the amount of matter in an object. It does not depend on where you are. Your mass is the same on Earth, on the Moon, and in outer space. Weight is the force with which gravity pulls you down, and weight depends on the strength of gravity, which changes from place to place. The person who first understood this distinction was Isaac Newton, and the understanding came to him, at least according to legend, in the garden of his family estate in Woolsthorpe, where he had fled from Cambridge to escape the plague in 1665. Newton's friend William Stukeley recorded his account. After dinner, when the weather was warm, we drank tea in the garden, in the shade of apple trees. He had a thought about gravitation. Why does an apple always fall straight down to the ground? Newton realized there must be a force pulling the apple toward the earth. Otherwise, why would it not fly sideways, or upward, or just hover in the air? He called this force gravity, from the Latin gravitas, heaviness, and he formulated a law that described it mathematically. The gravitational force between two bodies is proportional to the product of their masses and inversely proportional to the square of the distance between them. From this law follows a simple but profound conclusion. Weight is mass multiplied by the acceleration due to gravity. On the surface of the Earth, that acceleration is about 32 feet per second per second. But that about is not a constant. At the top of a mountain, you are slightly farther from the center of the Earth. Gravity is slightly weaker, and you weigh slightly less. At the equator, you weigh less than at the poles, because the Earth is spinning and centrifugal force partially offsets gravity. On the Moon, gravity is 6 times weaker, and you would weigh 6 times less with the same mass. One demonstrator ran a simple experiment. He weighed a piece of metal on extremely precise scales at the ground floor of a building, then went up to the roof and weighed it again. Downstairs it read about 5.7 grains. Upstairs, about 5.71. A difference of roughly 1/100th of a grain. The mass did not change. The weight changed, because on the roof you are slightly farther from the center of the Earth, and gravity is slightly weaker. And if you lifted that piece another 60 miles or so into space, it would weigh almost nothing. This distinction between weight and mass is critically important for understanding why the kilogram is such a difficult unit. When we say, Le Grand Quai weighs 1 kilogram, we actually mean its mass is 1 kilogram. Its weight in Paris is about 2.205 pounds force. In Tokyo, its weight would be slightly different, because gravity in Tokyo is slightly different. On the Moon, very different. That is exactly why redefining the kilogram through the Planck constant was so important. The Planck constant is not an object sitting in a specific gravitational field. It is a number, the same at any point in the universe. A kilogram tied to the Planck constant is a kilogram on Earth, on the Moon, on Mars, in deep space. It does not depend on gravity. It does not depend on anything except the fundamental properties of reality. Newton, who first understood the difference between weight and mass, could hardly have imagined what this would lead to 400 years later. But every time you step on a bathroom scale and see a number, remember that that number depends not only on the amount of matter in your body, but also on where on the surface of the Earth you are standing. At the equator you are lighter by a few ounces than at the poles, not because you lost weight, but because the planet is spinning. Alexandria, 3rd century BC, the most intellectually vibrant city on Earth. Founded by Alexander the Great, governed by the Greek descendants of one of his generals, standing at the crossroads of Egyptian, Greek, Persian, and Roman cultures. Here stood the great library, the largest repository of knowledge in the ancient world, where the finest thinkers of the era worked. And here lived Ctesibius, a man whose name most people have never heard, but whose invention we use every day. Ctesibius was the son of a barber. He grew up in the shop, surrounded from childhood by simple mechanisms, counterweights for mirrors that his father adjusted for customers, and he noticed that water in the barber shop dripped at a steady rate, as long as you kept the level in the container the same. By then, the Egyptians had been using water clocks called clepsydras for several thousand years. The simplest design, a bucket with a hole in the bottom, filled with water. The water drains out, and marks on the inside wall tell you how much time has passed. The problem, as I mentioned earlier, was that the flow rate depended on the water level. Full bucket, strong pressure, fast flow. Emptying bucket, weak pressure, slow flow. The clocks were uneven. Ctesibius solved this problem with an elegance that still impresses engineers today. He added a second reservoir above the main one. Water from the upper reservoir flowed continuously into the lower one, faster than it drained from the hole at the bottom. The excess overflowed back through a special drain. This way, the water level in the lower reservoir always stayed the same. The pressure remained constant, and the flow rate was uniform. The draining water collected in a third vessel, inside which a float with a pointer rode upward. As the vessel filled, the float rose, and the pointer moved along a scale, showing the time. For the first time in history, time was being measured continuously and uniformly, not by the sun, not by the stars, but by a mechanism. These were the world's first mechanical clocks. Ctesibius did not stop there. He turned his clocks into works of art and engineering. Gilded figures of gods pointed to the time. Complex gear systems allowed the scale to rotate slowly, showing not just the hour but the day of the month and the day of the year. Automatic figures moved and struck bells on the hour. In essence, these were the first striking clocks, 1,500 years before the cuckoo in a Swiss clock. The young Archimedes, the same Archimedes who would later become famous as the greatest mathematician of antiquity, came to Alexandria and studied the work of Ctesibius. He developed his ideas, adding even more complex mechanisms to water clocks. Arabic translations of Archimedes' works describe a clock with a gorgon's head whose eyes changed color every hour. Modern reconstructions reveal a device of astonishing complexity for its time. Ctesibius's water clock was installed in the Tower of the Winds in Athens, the first public weather and timekeeping station in history. An octagonal building with sundials on each face and a water clock inside. The citizens of Athens set their time by it, but the great library of Alexandria, where Ctesibius's writings were stored, burned several times during wars over the following 8 centuries. His works were lost. We know about them only from references in other authors' texts. Ctesibius himself was almost forgotten, even though his invention, the uniform measurement of time, changed civilization. And here we see the same pattern as with the meter and kilogram. A brilliant solution, a hidden flaw that reveals itself over time. Ctesibius's water clocks were remarkably accurate for their era, but water is a fickle medium. Temperature affects its viscosity, and therefore the flow rate. In winter, the water flows slightly slower, in summer, slightly faster. Mineral deposits clog the opening, and the flow slows. The float can stick. Gears wear out. More than 1,000 years passed before the next fundamental breakthrough in time measurement arrived. And it came not from water, but from metal. Ctesibius's water clocks were brilliant, but they had a limitation that grew more obvious as civilization became more complex. Water is a wonderful medium for slow, smooth timekeeping. But water cannot do one important thing. It cannot tick. It flows continuously. It has no discrete intervals. And for many purposes, for navigation, for coordinating actions, for scientific experiments, what you need is exactly a tick. A precise, repeating, countable beat. The transition from the continuous flow of water to the discrete ticking of mechanical clocks was one of the great conceptual leaps in the history of technology. And it did not happen all at once, but gradually, over several centuries. The key element was the so-called escapement. This is a device that converts continuous motion, the falling of a weight, the unwinding of a spring, into a series of identical, evenly spaced jerks. Each jerk is one tick. The escapement is what makes a clock a clock. Early mechanical clocks of the 13th and 14th centuries used what is called a verge, a vertical shaft with 2 paddles that alternately engaged the teeth of a gear wheel. The verge rocked back and forth, tick-tock, and each swing released the gear by exactly one tooth. The speed of the rocking determined the speed of the clock. But the problem was that the verge mechanism depended on friction, on the weight of the counterweights, on the quality of manufacture, and it was unstable. Clocks could gain or lose 15 minutes or more per day. The revolution came from Christian Huygens, a Dutch physicist, mathematician, and astronomer, in 1656. He replaced the verge with a pendulum. A pendulum has a remarkable property. Its period, the time for one full swing back and forth, depends almost entirely on the length of the pendulum and the force of gravity. It barely depends on amplitude, on how far the pendulum swings. This property is called isochronism, and Huygens was the first to use it to regulate a clock. Huygens's pendulum clocks were tens of times more accurate than verge clocks. Instead of 15 minutes of error per day, less than one. For the first time, it made sense to put a minute hand on a clock face. Before Huygens, clocks showed only hours, since minutes were meaningless at that level of error. After Huygens, minutes became real. The world got more precise. And here is something worth noticing. Right now, as you lie in the dark, you are experiencing time nothing like the way clocks show it. The minutes before sleep stretch or compress depending on your mood, your tiredness, your thoughts. Your internal time, subjective, warm, uneven, has nothing in common with the cold ticking of a pendulum. And yet, we built all of civilization on its rhythm, not ours. But pendulum clocks worked poorly on ships, since the rocking of the vessel threw off the pendulum. And it was at sea that precise clocks were needed most. Determining longitude, your position on the east-west axis, required knowing the exact time. If you know it is exactly noon in Greenwich, and the sun above you has not yet reached its peak, you can calculate how far west of Greenwich you are. But to do that, you need to know Greenwich time to the minute, and in the middle of the ocean there was no radio, no satellites, no Ruth Belville. The solution came from John Harrison, an English self-taught carpenter who spent 40 years of his life creating a marine chronometer, a clock that could keep time accurately through rolling seas, temperature swings, and humidity. His fourth model, H4, the size of a large pocket watch, lost only 5 seconds over 2 months of a transatlantic voyage in 1761. It was one of the greatest engineering triumphs of the 18th century, a triumph that saved thousands of sailors' lives previously lost to navigation errors. Harrison's chronometer is yet another example of how the pursuit of measurement precision transforms the world. Not abstractly, not theoretically, but literally. Sailors stopped dying because one stubborn carpenter learned to build a clock that was not afraid of waves. Precise measurement of time, in the most literal sense, saved lives. That is the path humanity traveled before Louis Essen in England began building his atomic clocks. From dots on a cave wall, to shadows on a sundial, to drops of water in Ctesibius's clepsydra, to the swing of Huygens's pendulum, to Harrison's spring chronometer, to the quartz oscillator, and finally, to the vibration of a cesium atom. Each step was a search for a more stable, more predictable, more constant tick. Each step was a move closer to the pulse of the universe itself. To understand what Essen did, we need to pause for a moment and think about this. Every atom of every element in the periodic table is unique, and one of the things that makes it unique is the set of frequencies at which it absorbs and emits energy. Think of an old radio with a frequency dial. At one frequency you hear one station, at another a different one. Atoms work in roughly the same way. Each one is tuned to its own frequencies. Hydrogen to some, carbon to others, cesium to yet others. These frequencies are determined by the structure of the atom, the arrangement of electrons, the properties of the nucleus, and they do not change. A cesium atom today vibrates at exactly the same frequency as it did 1 billion years ago, and it will vibrate at that same frequency 1 billion years from now. This is perhaps the most stable thing in the known universe, The idea of using atomic vibrations as the basis for measuring time was born in the early 20th century, but the technology to make it real appeared only after World War II. In America, at the National Bureau of Standards, work on atomic clocks was already underway with strong funding and large teams. Essen in Britain worked almost alone, on a minimal budget, in conditions where his laboratory's management did not particularly believe in his project. His first experiment literally exploded, destroying a significant portion of the equipment. But Essen kept going. In a classic underdog story, he built the world's first working cesium atomic clock, cesium-1. The principle was this. A beam of cesium atoms was passed through a region with microwave radiation. When the microwave frequency precisely matched the frequency of the transition between two energy levels of the cesium atom, the atoms responded. A detector picked up this response and used it as feedback to fine-tune the microwave frequency. Each time an atom made a transition, that was one tick of the clock. Cesium-1 was accurate to within 1 second in 300 years. For the middle of the 20th century, this was unprecedented. The second no longer depended on the rotation of the Earth. Time was locked into the heartbeat of a cesium atom, a motion so constant that no force in the universe could change it. In 1967, the official redefinition took place. The second was defined as the time it takes for a cesium-133 atom to complete 9,192,631,770 oscillations. That number seems absurdly long and random, but it is not random. It was chosen so that the new second would match the old one, the second based on the Earth's rotation at that time, as closely as possible. Modern cesium clocks work on a refined principle. Lasers slow cesium atoms to near complete stillness. A cloud of frozen atoms is tossed upward through a microwave chamber, passes through it, falls back, and passes through again. The double pass increases precision. The result? Clocks that lose 1 second in 138 million years. Think about that number. 138 million years is the time since the middle of the Cretaceous period, when tyrannosaurs walked the Earth. If you had started these clocks back then, today they would be off by exactly 1 second. And here is what that precision makes possible. In 1971, two physicists, Haffler and Keating, ran a famous experiment. They took 4 portable atomic clocks, bought 2 extra airline tickets for them on regular commercial flights, and carried the clocks around the Earth, first eastward, then westward. At the same time, identical clocks remained on the ground at the United States Naval Observatory. When the travelers returned and compared readings, the result was stunning. The clocks that flew east lagged behind the ground clocks by 59 nanoseconds. The clocks that flew west ran ahead by 273 nanoseconds. Time in the airplane had flowed differently than on the ground. This was not a clock error. This was confirmation of Einstein's theory of relativity. Time depends on speed. The faster you move, the slower time flows. A plane flying east added its speed to the Earth's rotation, and time slowed down for it. A plane flying west subtracted its speed from the Earth's rotation, and time sped up. The atomic clocks were precise enough to catch this difference, a difference predicted by equations Einstein had written 60 years earlier. The Haffel-Keating experiment deserves a few more words, not so much for the physics as for the picture it paints. Imagine 1971. 2 physicists from the United States Naval Observatory buy 4 portable atomic clocks. Each clock is about the size of a small suitcase, worth tens of thousands of dollars. Haffel and Keating buy 4 extra plane tickets, 1 for each clock, because the instruments need to be placed in passenger seats, not in the cargo hold, where vibrations might affect their readings. Flight attendants, passengers, pilots, everyone stares in amazement at 2 men buckling suitcases into seatbelts and talking to them like patients. Haffel later recalled that one pilot, learning the purpose of the experiment, offered to help. He could slightly alter the course or altitude to optimize the relativistic effects. Haffel politely declined. The purity of the experiment was more important. They flew around the Earth twice, first east, then west. Total time in the air was about 120 hours. When they returned and compared their traveling clocks to the clocks that stayed at the observatory, the results matched the predictions of relativity to within about 10%. Time in the aeroplane really had flowed differently. Without atomic clocks of this precision, there would be no GPS. Global navigation satellites determine your position by measuring the time it takes for a radio signal to travel from a satellite to your phone. The signal moves at the speed of light, about 186,000 miles per second. At that speed, an error of 1/1,000,000th of a second means an error of almost 1,000 feet. And the satellites fly at an altitude of about 12,400 miles and move at about 8,700 miles per hour. And for them, according to Einstein, time flows differently than for us on the surface. The clocks on GPS satellites run faster than clocks on Earth because they are farther from the center of the planet and gravity is weaker up there. The difference adds up to about 38 millionths of a second per day. If this were not corrected, navigation error would reach about 7 miles after 1 day. After a week, GPS would be useless. So each GPS satellite's clock is deliberately slowed down at the factory to compensate for the relativistic speed-up it will experience in orbit. The clocks are intentionally made wrong on Earth, so they will be right in space. Every time you open a map on your phone and see a blue dot showing where you are using atomic clocks and the theory of relativity. Both are consequences of humanity's drive to measure time more precisely. Let us briefly return to the story of time and tell an episode that beautifully illustrates how valuable precise time was before the era of radio and internet. In the early 19th century, London was the largest city in the world. Banks, stock exchanges, docks, factories, all depended on precise time. But clocks in different parts of the city showed different times. Some ran fast, others slow. Others were correct in the morning but drifted by several minutes by evening. For a stockbroker who needed to record a trade at the precise minute, or a ship captain preparing to set sail, inaccurate clocks meant lost money. The Greenwich Observatory, perched on a hill above the Thames, was the only place in London where the time was truly precise. Astronomers determined it by the stars and the sun, using methods refined over centuries. Every day at 1 in the afternoon, a red ball atop the observatory dropped, a visual signal for ships on the Thames, allowing them to calibrate their chronometers. But what about those who could not see the Greenwich ball? For that, there was the Belleville family. Starting around the 1830s, John Henry Belleville climbed the hill to Greenwich every week, synchronized his pocket chronometer with the observatory's precise time, then came back down into London and visited his clients. Watchmakers, jewelers, bankers, steamship companies. For a fee, he let them synchronize their clocks with his chronometer. He was literally selling time. After John's death, his daughter Ruth inherited the business, continuing the rounds until 1943, when radio time signals made her services unnecessary. By then, she was 86 years old and had been in the business for more than half a century. Her chronometer, a pocket watch made by John Arnold back in the 18th century, became legendary. She carried it wrapped in several layers of cloth, protecting it from bumps, temperature changes, from anything that might affect its accuracy. When the British Post Office began distributing precise time over telephone lines in 1908, the Bellevilles had to fight for their clients. Some London watchmakers claimed that their personal time from Ruth Belleville was more accurate than the telephone signal. The dispute reached the newspapers. Ruth became a minor celebrity, the woman who sells time to London. She continued her rounds despite competition from radio and telephone because she had loyal clients who trusted her chronometer more than an electrical signal. This story is about trust. Time is not just a number on a dial, it is a system of trust. You trust that the clock on the wall shows the right time. The clock trusts the quartz oscillator inside. The oscillator trusts the signals synchronized with atomic clocks. The atomic clocks trust the vibration of a cesium atom. And the vibration of a cesium atom is, as far as we know, the most reliable thing in the universe. The whole chain, from your glance at the clock to the trembling of an atom, is a chain of trust. And if a single link breaks, the system stops working. Ruth Belville was a living link in that chain, between the Greenwich Observatory and London's watchmakers. When technologies replaced her, radio, telephone, later the internet, the principle did not change. Only the medium changed. Instead of a woman with a chronometer, an electromagnetic wave from atomic clocks. But the essence is the same. Someone, somewhere, must keep precise time and pass it on to everyone else. That someone used to be a person. Now it is an atom. But the chain of trust still exists. Maxwell was a Scottish physicist whom many consider the most influential scientist of the 19th century, on par with Darwin and perhaps above. His equations of electromagnetism, 4 formulas that describe all the behavior of electric and magnetic fields, are still taught in every university in the world without a single change. Maxwell showed that light is an electromagnetic wave and calculated its speed from purely electrical and magnetic constants. When the number he got matched the experimentally measured speed of light, it was one of the great moments in the history of physics. And Maxwell said something else. Something that in his time sounded almost fantastical. He said, "If we want standards that are truly constant, we should look for them not in the dimensions or the motions of our planet, but in the wavelength, the period of vibration, and the mass of imperishable, unchanging, and perfectly identical molecules." Maxwell proposed tying the meter to the wavelength of a specific color of light. Each color is an electromagnetic wave with a specific wavelength. Red light has a wavelength of about 28 millionths of an inch. Violet, about 16 millionths. If you take the light of a specific element, say a particular spectral line of krypton, its wavelength will be the same at any point in the universe. Count how many wavelengths fit into a meter, or about 3 feet 3 inches, and you have a definition of the meter that depends on no rod, no object. The problem was that Maxwell could not do it. The technology of his time did not allow a precise enough measurement of wavelength. Between his idea and its realization lay decades. The man who began turning Maxwell's dream into reality was Albert Michelson, an American physicist obsessed with the precision of optical measurements. Michelson worked at the International Bureau of Weights and Measures in Sèvres, the very place where Le Grand Quai was kept. He built interferometers, devices that split a beam of light, send it along 2 different paths, and then recombine it. When the 2 beams meet, they create a pattern of light and dark bands, an interference pattern. From this pattern, the difference in path lengths, and therefore the wavelength itself, can be determined with incredible precision. Michelson spent decades refining his instruments. His work was painstaking, almost monotonous, endless series of measurements, counting bands, recalculating, rechecking. But the results were revolutionary. For the first time, it became possible to tie a visible length, a meter, to something invisible to the eye, the wavelength of light. On October 14, 1960, delegates from around the world, including representatives of the Soviet Union and the United States, in the thick of the Cold War, gathered in Sèvres. At 6 in the evening, to applause from the hall, the meter was redefined. It was now measured not by the length of a platinum bar, but by the number of wavelengths of orange-red light emitted by a special krypton lamp. 1,650,763.73 wavelengths. The platinum bar of Machine and Delambre, with its hidden error, was sent to a museum. The meter had become immaterial, tied not to an object but to a property of nature. But the krypton lamp, for all its virtues, was not ideal. The krypton's spectral line had a certain width, meaning the light was emitted not at one exact frequency but over a narrow range. This limited precision. What was needed was a light source with an absolutely precise, fixed wavelength. And in 1960, almost simultaneously with the redefinition of the meter, California physicist Theodore Maiman switched on the world's first laser. The word laser is an acronym: Light Amplification by Stimulated Emission of Radiation. A laser produces light of a perfectly precise wavelength, and that is exactly what makes it the ideal instrument for measuring distances. The principle is simple. Aim a laser beam at an object. Measure the time it takes for the reflected beam to return. Knowing the speed of light, calculate the distance. The more precisely you know the speed of light, and the more precisely you measure the time, the more precisely you determine the distance. On July 21, 1969, Neil Armstrong and Buzz Aldrin left a special mirror on the surface of the Moon, a retroreflector. It is a set of corner reflectors that send light back exactly in the direction it came from. When astronomers aimed a laser pulse at this mirror, the light returned in 2.5 seconds. For the first time, the distance to the Moon was measured to within about an inch. Thanks to these measurements, we know the Moon is moving away from the Earth at a rate of about 1.5 inches per year. The laser and atomic clocks made the next logical step possible. If you can measure both the speed of light and time with incredible precision, why bother defining the meter separately? Why not just say, a meter is the distance light travels in a certain fraction of a second? Then the meter would be expressed through the speed of light and the second, both tied to fundamental constants. That is exactly what happened in 1983. The meter was defined as the distance light travels in a vacuum in 1,299,792,458th of a second. The number looks unwieldy, but behind it is a beautiful idea. The speed of light is exactly 186,282.397 miles per second, by definition. No more, no less. Forever. Time and distance, which our ancestors measured by the shadow on a sundial, turned out to be inseparably linked by one of the most fundamental constants in the universe, the speed of light. Think about this. The last time you used a navigation app in your car or on your phone, you were, without knowing it, using the speed of light, atomic clocks, and Einstein's theory of relativity. All of it working together to show you where to turn right. 5,000 years from a knotted rope to a blue dot on a screen, and the entire chain holds because we learned to measure time and distance precisely. Of the 7 base units, 4 were now tied to the laws of physics. The second to the cesium atom, the meter to the speed of light, the ampere to the charge of the electron, the Kelvin to the Boltzmann constant. The last bastion of the old world remained, the kilogram, that same Le Grand K, losing weight in its Parisian basement. And to replace it, scientists had to carry out one of the most ambitious and longest-running experimental races in the history of science. A race between 2 approaches, one American, one German. One used electricity, the other counted atoms. Both seemed like madness. Both took decades, and both ultimately produced a result that had seemed impossible. Let us linger on the laser, because its story is one of the most remarkable in 20th century science, and it is directly connected to how the meter took its current form. When Theodore Maiman built the first working laser in 1960, many scientists and journalists did not understand what it was for. The laser was called a solution looking for a problem, a brilliant physical device with no obvious application. Maiman demonstrated that a ruby rod, illuminated by a flash lamp, emitted a narrow beam of coherent red light. Light in which all the photons moved in the same direction, with the same wavelength, in the same phase. Beautiful. But what do you do with it? The answer came quickly and from everywhere. Over the following decade, lasers penetrated medicine, industry, communications, surveying, and of course metrology. Their property, light with an absolutely precise, fixed wavelength, made them ideal instruments for measuring distance. The most famous laser ranging experiment took place on July 21, 1969, when Neil Armstrong and Buzz Aldrin placed a retroreflector on the surface of the Moon, a panel of special corner mirrors. Each mirror is made of 3 perpendicular surfaces forming the inner corner of a cube. This design has a remarkable property. Light hitting it at any angle is reflected back precisely toward the source. No matter where the laser aims, the reflection flies back to the sender. When astronomers aimed a laser pulse at this reflector from Earth, the light returned in 2.5 seconds. 2.5 seconds is the time for light to travel the round trip from Earth to Moon and back, roughly 477,000 miles. From this travel time, the distance to the Moon was calculated to within about an inch. For the first time in history, the distance to a celestial body was known not approximately, not about 239,000 miles, but precisely, with an error no bigger than a ruler you could hold in your hands. This experiment continues to this day. Astronomers regularly shoot a laser at the lunar mirror and measure the response time. Thanks to this, we know the Moon is moving away from Earth at about 1.5 inches per year. We know the Moon's orbit is not circular but elliptical, and the distance changes by about 26,000 miles between perigee, the closest point, and apogee, the farthest. We know this to the precision of fractions of an inch. A laser, a reflector, and atomic clocks. That is the entire toolkit. By the way, you can measure the speed of light at home using a microwave oven and a chocolate bar. This is not a joke. It is a real experiment that works. Remove the turntable from your microwave, place a chocolate bar on the floor of the oven, and run it for a few seconds. Microwaves are electromagnetic waves that travel at the speed of light. They form a standing wave inside the oven, and at the spots where the amplitude is highest, the chocolate starts to melt. You will get several melted spots spaced evenly apart. The distance between neighboring spots is half the wavelength of the microwave radiation. Double that distance and you get the full wavelength. The microwave frequency is usually printed on the back panel, typically 2.45 gigahertz. Multiply the wavelength by the frequency and you get the speed. The result will be approximate, plus or minus 20%, but the order of magnitude will be right. About 186,000 miles per second. 186,000 miles per second, or to be precise, 186,282.397 miles per second. That number is not the result of a measurement. It is a definition. Since 1983, the speed of light is exactly that much, by definition. The meter adjusts to fit it, not the other way around. And here is a subtle but crucial shift in thinking. Before 1983, the speed of light was a measured quantity. Scientists kept running more and more precise experiments. But in 1983, the speed of light stopped being measured. It became defined. If tomorrow someone builds a more precise instrument and discovers that the meter defined through the speed of light does not quite match the old platinum bar meter, the problem will not be with the speed of light. The problem will be with the old bar. The speed of light is exact by definition. The meter adjusts. The speed of light is the last constant in our story to which one of the 7 base units is anchored, and it closes the circle. Time is tied to cesium, distance is tied to time and the speed of light. Mass is tied to the Planck constant, electric current to the charge of the electron, temperature to the Boltzmann constant, amount of substance to Avogadro's number, luminous intensity to the photometric equivalent. 7 units, 7 constants, a system that describes everything. And every element of this system, at every stage of its history, contained a hidden error, and every error led to the next discovery. By the early 2000s, the situation with the kilogram had become genuinely awkward. Every other base unit, the second, the meter, the ampere, the Kelvin, had already been tied to fundamental properties of nature. They could be reproduced in any laboratory in the world, on any continent, on any planet if it came to that. But the kilogram was still defined as the mass of a specific lump of metal in a specific basement in a specific building on the outskirts of Paris. If Le Grand Quai were destroyed by fire or earthquake or simple human carelessness, the world would literally lose the kilogram. There would be no way to recreate it because the kilogram was that object. A way had to be found to tie mass to something indestructible, to a law of physics, to a number that is the same everywhere and always. But which one? 2 international projects, each audacious in its own way, took on the challenge at the same time. One was based in America, the other in Germany. They used completely different approaches but were aiming for the same goal, to define the kilogram without a physical standard. The American team worked with the so-called watt balance, located about 20 miles north of Washington, in a lab at the National Institute of Standards and Technology. These scales were one of the most sensitive measuring instruments on the planet. So sensitive that the entire area around the lab was a no-car zone, because the magnetic field from the metal in vehicles could affect the readings. Almost everything inside the building was made of wood and covered in vinyl. Every metal object brought into the lab, down to the smallest screw, was checked for magnetism. The principle of the watt balance was elegant. In essence, it was the same beam balance used 5,000 years ago in Mesopotamia, but instead of weights on the second pan, electromagnetic force was used. On one pan went a copy of Le Grand Quai, on the other, a coil placed in a magnetic field. When electric current was passed through the coil, it created a force that counterbalanced the mass on the first pan. The precise amount of electrical energy needed to balance a kilogram became the new definition. Sounds simple. In practice, a nightmare. The scales were so sensitive they responded to the phases of the moon, to the groundwater level beneath the building, to a herd of deer moving through the nearby forest, to vibrations from trucks driving several miles away. Each of these factors had to be measured, accounted for, and compensated. Stefan Schlamminger, one of the project leaders, said, "To measure a kilogram to 4 parts in 100 million, you need to measure every auxiliary quantity, voltage, resistance, gravity, velocity, with even greater precision." The art lay in holding all these threads at once. The project lasted more than 30 years. The first researchers who started it had long since retired. But the younger generation carried on, step by step, closing in on the goal, defining the kilogram through electrical power. 4,000 miles to the east, in Germany, a completely different team was at work. Team Silicon Sphere. Their approach was even bolder. They wanted to count every atom in a perfect sphere of silicon. The idea was conceptually simple. Take a piece of pure silicon, shape it into a perfect sphere, measure its dimensions with incredible precision, determine the distance between silicon atoms in the crystal lattice, which can be done with X-ray diffraction. Knowing the volume of the sphere and the spacing between atoms, count the total number of atoms. Knowing the number of atoms and the mass of a single atom, you get the precise mass of the sphere. And from that, you can define the kilogram by atom count. It sounds like cover the entire Earth with sand and count every grain. The scale of the task was roughly that. A kilogram of silicon contains about 21 septillion atoms. 21 followed by 24 zeros. Of course, nobody counted them one by one. They counted through geometry, dividing the volume of the sphere by the volume of one unit cell of the crystal lattice, getting the number of cells, and from that, the number of atoms. But for this, a sphere of absolutely perfect shape was needed. No machine on the planet could provide the required level of precision. The solution was found in the hands of one man, an Australian optical lens polisher named Achim Leistner. This man had such a refined sense of touch that, as colleagues said, he could feel the atomic structure of the silicon surface with his fingertips. He polished the sphere by hand for months, bringing it to a level of perfection such that, if the sphere were the size of the Earth, the tallest mountain on it would be only a few fractions of an inch high. And when the sphere was nearly finished, disaster struck. Natural silicon consists of three isotopes: silicon-28, silicon-29, and silicon-30. Each isotope has a slightly different mass. If the sphere contains a mix of all three, it is impossible to precisely determine the mass of a single atom, because one silicon atom could weigh differently depending on which isotope it is. Pure silicon-28 was needed. The solution came from an unexpected source. The Cold War had ended, and in Russia, centrifuges once used for enriching uranium sat idle. The same centrifuges that had separated uranium isotopes for nuclear weapons could now be used to separate silicon isotopes. A new batch of silicon was shipped to Russia, run through the centrifuges, and came back as silicon-28, with a purity above 99.99%. From it, a new blank was made, and Achim Leistner started polishing all over again. Both teams, the American watt balance and the German silicon sphere, worked independently but moved toward the same goal: to define the kilogram to 8 decimal places. 8 places is 100 millionth. That level of precision meant that if you were weighing all the water on Earth, the error would be roughly one swimming pool. In November of 2018, at the General Conference on Weights and Measures in Versailles, delegates from 60 countries voted on the new definition of the kilogram. It was now defined not by a lump of metal, but by the Planck constant. The value of this constant was fixed precisely to more than 30 decimal places. Any laboratory in the world with sufficiently precise equipment could now reproduce the kilogram without ever consulting the Parisian basement. On May 20th, 2019, the new definition took effect. Le Grand K, that elegant cylinder of platinum and iridium that had lived in a basement for over 130 years, was officially retired. It still lies in its place, behind 3 layers of glass, in a building no occupier ever dared to seize. But now, it is a museum piece, a relic. The kilogram no longer needs it. We mentioned the silicon sphere, but it is worth telling its story in more detail, because it has an unexpected twist connected to another fundamental unit: the mole. The mole is perhaps the most mysterious of the 7 base units for anyone who does not work in chemistry. Chemistry students worldwide dread the mole, but its idea is actually quite simple. The word mole comes from the Latin moles, meaning heap, and a mole is just a very, very large number. Just as a dozen is 12, a mole is roughly 6.022 times 10 to the 23rd power. 602 sextillion. A number so enormous the human brain cannot picture it. Why do we need such a number? Because atoms are unimaginably small. A single carbon atom weighs roughly 2 times 10 to the negative 23rd power of a gram. A chemist cannot work with individual atoms. They are invisible, impossible to pick up with tweezers, impossible to put on a scale. But if you take a mole of carbon atoms, those same 6 times 10 to the 23rd, their combined mass works out to exactly 12 grams, about 4/10 of an ounce. The number 12 is the atomic mass of carbon, as listed in the periodic table. The mole lets you translate the world of atoms into the world of grams. It is a bridge between the microscopic and the macroscopic. If the silicon sphere team could precisely count the atoms in 1 kilogram of silicon, that automatically gave the precise value of Avogadro's number. A single experiment could redefine 2 units, the kilogram and the mole. That is exactly what happened in 2019. Avogadro's number was fixed at 6.022140076 times 10 to the 23rd power, period. No more approximately. The mole became as precise as the second or the meter. On February 4, 1904, a fire broke out in the American city of Baltimore. A warehouse in the business district caught flame. Local firefighters rushed to the scene, but the fire spread too fast. Reinforcements were called from Washington and New York, cities less than 200 miles away. Fire crews raced in. They unrolled their hoses and discovered that their hoses did not fit Baltimore's hydrants. Different cities used different equipment standards, different diameters, different threads, different couplings. Firefighters from neighboring cities could only stand and watch the city burn. For 2 days, the fire raged out of control. 1,500 buildings were destroyed, 70 blocks turned to ash. Losses ran into hundreds of millions of dollars. On July 23, 1983, both engines of a Canadian Boeing 767 operating Flight 143 from Montreal to Edmonton fell silent at an altitude of about 40,000 feet. Both at the same time. The tanks were bone dry. How did this happen? Canada at the time was transitioning from the imperial system to the metric system. The aircraft was one of the first in Air Canada's fleet equipped with metric fuel gauges. But the ground crew still thought in pounds. When they needed to load 49,200 pounds of fuel, they confused pounds and kilograms. Since 1 kilogram equals about 2.2 pounds, they loaded roughly half the fuel needed. The captain, Robert Pearson, was a former glider pilot. When both engines quit and the plane became a 280,000-pound glider, Pearson remembered skills that once seemed useless for a jet pilot. He steered the machine toward an abandoned military airfield in the town of Gimli, Manitoba. No engines, no hydraulics, partially functioning instruments. He landed the plane on a former runway that was being used that day as a go-kart track. There were people on the strip, families with kids who had come for the races. By some miracle, no one died. The plane stopped a few dozen yards from spectators. The incident entered aviation history as the Gimli glider. 15 years later, another disaster caused by a mix-up in units. In 1998, NASA launched the Mars Climate Orbiter toward Mars. The flight lasted more than 9 months. The spacecraft approached Mars and was supposed to enter orbit. Instead, it came in too low and burned up. The investigation revealed that one engineering team, the subcontractor Lockheed Martin, was transmitting thrust data in pound force, while NASA's Jet Propulsion Laboratory was receiving those numbers as newtons. A pound force is about 4.5 newtons. The discrepancy accumulated over the entire flight, and by the time the spacecraft reached Mars, its trajectory was off by dozens of miles. A $125 million satellite was lost because of a mix-up between two systems of measurement. Even Napoleon's height became a victim of unit confusion. For a long time, his height was listed as roughly 5 feet 2 inches, cementing his reputation as short. A psychological complex was even named after him, but his height had been recorded in French inches, which were longer than English inches. Converted properly, Napoleon stood about 5 feet 7, a perfectly average height for a man of his era, a bit taller than Pushkin. The same error that destroyed the Mars satellite and nearly killed passengers on a Canadian airliner, except this time it stole 5 inches from a man's height. Every one of these stories is about the same thing. Measurements only work when everyone uses the same system. The moment a gap appears, between pounds and kilograms, between French and English inches, between different hose standards, the consequences can be catastrophic. There is a historical episode that sounds made up, but is apparently based on real events. It explains why the United States still has not adopted the metric system, and it involves pirates. In 1793, France sent a scientist named Joseph Dombey to America, carrying a copper meter standard and a copper kilogram standard. The ship was bound for Philadelphia, then the capital of the United States. But in the Caribbean, the ship was caught in a storm, blown off course, and seized by British privateers, or by pirates, depending on the version. Dombey was taken prisoner and died in captivity in the Caribbean. The standards never reached America. If Dombey had made it, Thomas Jefferson, then Secretary of State and a great admirer of French ideas, might have persuaded Congress to adopt the metric system. America would have been metric from the start. But the standards were lost, the moment passed, and Americans were left with their inches, feet, pounds, and gallons. Napoleon's conquests are what spread the metric system across Europe. Not persuasion, not scientific arguments, not trade advantages, but military occupation. Napoleon conquered a country and imposed French laws on it, including metric units. Look at the map of metric adoption, and it almost perfectly matches the map of Napoleonic conquests. Holland, Belgium, Italy, Germany, Spain all received the metric system from Napoleon. And the countries that resisted him, England and Russia, stayed with their old measures for a long time. America, Myanmar, and Liberia are the three countries that still have not officially adopted the metric system. And every time you see a TV screen size in inches or a highway sign in miles per hour, you are witnessing the consequences of that Caribbean storm and those pirates who intercepted the ship with the meter and kilogram standards over 230 years ago. Picture a hall in Versailles, not the Palace Versailles, though it is nearby, the conference hall of the International Bureau of Weights and Measures. Delegates from 60 countries, physicists, metrologists, diplomats. November of 2018, the General Conference on Weights and Measures, an event held once every 4 years that sounds so dull that newspapers almost never cover it. But this time, everything was different. A proposal decades in the making was put to a vote, the simultaneous redefinition of 4 of the 7 base units. The kilogram through the Planck constant, the ampere through the elementary charge of the electron, the Kelvin through the Boltzmann constant, the mole through Avogadro's number. The meter and the second had already been redefined earlier through the speed of light and the cesium frequency. The candela had also already been tied to a physical constant. For the first time in history, all 7 base units were to be anchored to fundamental constants of nature. Not one of them would depend any longer on a specific object, a specific place, a specific moment in time. They would become eternal as the laws of physics themselves. The delegates voted. One by one, country by country, representatives stood and said, yes. Unanimously. 60 countries, not a single vote against. The decision was adopted. On May 20th, 2019, World Metrology Day, the new definitions took effect. When the new definitions took effect, nothing changed and everything changed. Nothing changed in the sense that a bag of sugar at the corner store weighed the same as the day before. A yard of fabric did not get longer. A second did not stretch or shrink. But everything changed in a fundamental sense. For the first time in history, the entire system of units became reproducible from first principles. If every standard in the world were destroyed, every platinum bar, every silicon sphere, every atomic clock, the system could be rebuilt from scratch. Because the definitions are no longer tied to objects, they are tied to numbers. And numbers cannot be destroyed. If humanity ever sends a ship to another star, there will be no need to carry a meter standard or a kilogram standard on board. All that is needed is a record of the physical constants, written on any medium, paper, electronic memory, or engraved on a gold plate like the one on the Voyager probe. From those numbers, colonists will be able to reproduce the entire system of units, build any instruments, calibrate any devices. The system that started with the length of a pharaoh's arm has traveled quite a long way. Here is what is curious. We redefined the meter through the speed of light, the kilogram through the Planck constant, the second through the vibrations of an atom. We detached these units from the human body and tied them to the laws of the universe. But the units themselves stayed at a human scale. A meter is still roughly 1 step. A kilogram is still roughly a quart bottle of water, about 2.2 pounds. A second is still roughly 1 heartbeat. That is no accident. When the French revolutionaries chose 1/10,000th of a quarter of the meridian, they cared, among other things, about making the new unit convenient for everyday life. The meter had to be proportional to a person, not too big, not too small. Something you could show with your hands, picture visually, apply to fabric, to a road, to a field. There are other unit systems tied not to humans but directly to physics. The most famous is Planck units, proposed by Max Planck at the start of the 20th century. The Planck length is roughly 10 to the negative 35th power of a meter. That is so small that even a proton is a giant next to it. Planck time is roughly 10 to the negative 43rd power of a second. That is the shortest interval of time for which our physics equations make sense. Planck units are elegant for theoretical physics. In them, the fundamental constants, the speed of light, the gravitational constant, the Planck constant, all equal 1. Equations simplify. Einstein's famous equation E equals mc squared becomes, in Planck units, simply E equals m. Mass and energy are the same thing, which is exactly what Einstein was trying to say. But try ordering coffee in Planck units. A cup measuring 7 googles of cubic Planck lengths. The mass of the coffee, 14 million Planck masses. Brewing time, about 2 times 10 to the 100th power Planck time units, which in our terms is about 2 minutes. Not very handy. We use meters, kilograms and seconds, not because they are ideal in an abstract sense. We use them because they fit us. They match our bodies, our experience, our everyday reality. They were born from our bodies, and no matter how far we go in redefining them, no matter how deeply we tie them to quantum physics and the speed of light, their scale remains human. The ancient Greek philosopher Protagoras said, "Man is the measure of all things." 2,500 years later, that statement remains surprisingly accurate, though not at all in the sense Protagoras intended. We have measured the universe, from the Planck length to the observable edge of the cosmos. But the scale we use, we chose to fit our own bodies. And maybe there is truth in that. Because measurement is not just a technical procedure. Measurement is the way a human being enters into dialogue with the universe. We ask, how much? And the world answers. But the answer depends on the units in which we frame the question. And we frame it in units that make sense to us, in steps, in palms, in heartbeats. Then, when we need greater precision, we find in nature clocks more constant than our hearts and rulers straighter than our arms. But we do not forget where we came from. There is one aspect of the history of measurement that rarely gets thought about, and yet it is perhaps the closest to each of us. It is how the measurement of time changed the very fabric of everyday life. Not scientific life, not industrial life, but ordinary human life. For thousands of years, people lived without any concept of exact time. Morning began when the sun rose, work ended when the sun set. Lunch was when you felt hungry. Meetings were set for dawn, for noon, for sunset, not for 3:15. The first mechanical clocks on city towers became the soundtrack of medieval life. The bells struck every hour, and townspeople began aligning their affairs to this rhythm. But the clocks were inaccurate, 15 minutes of error per day, and nobody took their readings too seriously. Roughly noon, roughly 1, that was enough. Everything changed with pendulum clocks in the 17th century and pocket watches in the 18th. When time became personal, portable, available to everyone, society restructured itself. Workers started arriving at factories at a set hour. Trains departed on schedule. School lessons lasted a fixed number of minutes. Life became partitioned, portioned, measured. Right now, at this very moment, you have a chance to briefly return to that older feeling. You are lying in the dark. No clocks in sight, no schedule. No need to rush anywhere. The time you are experiencing right now is the time of your body, your breathing, your heartbeat. The oldest clocks on Earth. The very ones from which the second was once born. Here is one more detail worth mentioning before we wrap up. We talked about how our senses are poorly suited for precise measurement, how we cannot tell by feel which of two objects is heavier, how we confuse size with weight, how vision and touch deceive us. There is a neat experiment that was conducted at Borough Market in London. People were given a set of weights of different shapes and sizes and asked to arrange them from heaviest to lightest. Almost everyone got it wrong. Almost everyone picked the largest weight as the heaviest, even though the heaviest was actually a small, dense cylinder. When people were shown the correct answer and given both weights to hold at the same time, they still could not believe the small one was heavier. This is not stupidity. It is a feature of our brains. Vision dominates touch. If the eyes say big, the brain interprets that as heavy. You need scales to override this illusion. That is exactly why scales were invented so early, 5,000 years ago in Mesopotamia. We needed an instrument that compensated for our own unreliability. And in this lies the deep irony of the entire history of measurement. We, creatures with approximate senses, learned to create instruments of unimaginable precision. Our eyes cannot distinguish millionths of an inch, but our interferometers can. Our touch cannot feel billionths of an ounce, but our scales can. Our sense of time is unreliable. Ask anyone who waited 5 minutes in a line and 5 minutes on a roller coaster, and they will tell you those were two completely different 5 minutes. But our clocks mark every second identically. We created instruments more precise than ourselves. In the past few years, humanity has produced more information than in all of preceding history. Data centers consume electricity on the scale of small countries. Every sensor, every camera, every phone generates streams of data. And all of it, bits, bytes, megabytes, gigabytes, cannot be expressed through the 7 base units. A bit is not a length, not a mass, not a time, not a current, not a temperature. A bit is a logical choice, 0 or 1. It has no physical dimension in the usual sense. Information cannot be weighed, cannot be measured with a ruler, cannot be timed with a stopwatch. And yet, information exists in the physical world. A bit is stored as a charge in a transistor, as magnetization on a disk, as a pulse of light in a fiber optic cable. Einstein's famous equation E equals mc squared says that mass and energy are interchangeable, which means information can be converted into mass. Your smartphone, when fully charged, weighs roughly half a nanogram more than when it is dead. A negligible difference, but not zero. The energy stored in the battery literally weighs something. Will an 8th base unit for information ever be introduced? Probably not, because a bit, strictly speaking, does not need a physical dimension. It is a logical construct, not a physical one. But the very existence of the question shows that the system of 7 units, elegant as it is, may one day prove insufficient. The world is changing. But for now, our 7 units are enough. From them, everything we need is derived. Newtons and pascals, volts and hertz, joules and watts. 7 numbers from which a description of everything that exists is built. 7 letters in the alphabet of the universe. And you know what unites these 7 letters? Each one was once an error. Each was born imperfect. And each, through centuries of corrections and redefinitions, became what it is today, a little more precise than yesterday, a little less precise than tomorrow. That is the whole story we have walked through, from grain to quantum, from shadow on sand to the vibration of an atom, from the pharaoh's arm to the speed of light. Now we can stop. Let us return to where we started, to you, to this room, to this night. Right now, atomic clocks all over the world are counting seconds. Each second, 9,192,631,770 oscillations of a cesium atom. Clocks are ticking at the National Physical Laboratory in England, at NIST in Colorado, at the Physikalische Technische Bundesanstalt in Braunschweig, in dozens of other laboratories. Their readings are collected and averaged, and from that average comes UTC, Coordinated Universal Time, the time by which the internet runs, planes fly, and rockets launch. At an altitude of about 12,400 miles above you, GPS satellites carry atomic clocks on board and continuously transmit their signal. Your phone picks up those signals, even if it is lying on the nightstand with the screen dark, and from the time differences between signals from several satellites, it figures out exactly where on the surface of the Earth you are. To within about 3 feet, sometimes to within an inch. This entire system, satellites, clocks, signals, computations, depends on the precision of the second. If the clocks on the satellites were off by 1/1,000,000th of a second, navigation would be useless. If the speed of light were defined with less precision, the meter would drift. If the Planck constant were fixed inaccurately, kilograms would diverge across the globe. Everything is connected to everything. Pull one thread and the whole structure stirs. But the structure holds. It holds because tens of thousands of people over 5,000 years, from an Egyptian surveyor with a rope to a physicist with a laser, did the same thing. They asked, "How much?" and worked to get an answer just a little more precise than the one before. Each generation stood on the shoulders of the last. Each error became a stepping stone. Each limit became a challenge. Machine died believing his error was a catastrophe. He could not know that 200 years later, the meter would be tied to the speed of light and his platinum bar would become a museum piece. He could not know that his tragedy was part of a long chain in which every inaccuracy pushes the world toward the next breakthrough. Ctesibius could not know that his water clock was the distant ancestor of the atomic clocks orbiting Earth. The Egyptian surveyor could not know that his knotted rope was the great-great-grandmother of the laser rangefinder. The Sumerian trader counting barley grains could not know that one day mass would be defined by a constant that cannot be seen, touched, or destroyed. They all did the same thing. They measured the world. And every one of their measurements was imperfect. And every imperfection led to the next step. Right now, above you, a sky full of stars, even if you cannot see them through the clouds or the city glow. The same stars our ancestors painted as dots on a cave ceiling 17,000 years ago. The same Pleiades that marked the start of the year. The same rhythms that were once our only clocks. We have come a long way from the cave. We learned to hear the vibrations of individual atoms and to see light reflected from a mirror on the moon. We defined 7 units that can describe everything, from quarks to quasars, from neutrinos to galaxy clusters. And we anchored those units to laws that depend on no object, no place, no moment in time. But one thing has not changed. The scale of our units is still our scale. A meter, 1 step. A kilogram, 1 palm. A second, 1 heartbeat. We measure the universe by ourselves. We are the measure of all things. Imperfect, approximate, but the only measure we have. Your heart is beating roughly once per second. Your step is roughly a yard. The bottle of water on your nightstand weighs roughly 2 pounds. The entire grand system that took 5,000 years to build starts and ends here, in your body, in this room, at this moment. The people who built this system, Mechain and Delambre, Ctesibius and Lavoisier, Essen and Michelson, Planck and Einstein, they were the same as you, imperfect, prone to error, stubborn, curious. Each one saw a limit and kept going. Each one found a mistake and used it as a door. You do not need to remember everything we talked about. You do not need to hold in your head 9 billion cesium oscillations or 30 digits of the Planck constant. All of it will keep working without you, quietly, reliably, invisibly. The atoms will vibrate, the light will travel, the clocks will tick. And you can just lie in the dark and breathe, roughly once per second, roughly. And that is enough. Let the thoughts soften. Let the numbers dissolve. Let the stories of Mechain and his secret, of Ctesibius and his drops of water, of Le Grand Quai in its Parisian vault, let all of it settle next to you, like a quiet hum, like a distant bell from a clock tower, like a whisper you do not need to hear in full. The world has been measured. The world is being measured right now. And it will keep being measured, each day a little more precisely, each year a little deeper, each century a little closer to that unreachable, beautiful, ever-receding precision we have been chasing since the first time we looked up at the sky and tried to count the stars. Everything is all right. The clocks are running. The world is in its place. You can let go. There is one more thought worth carrying with you into sleep. We said that units of measurement were born from our bodies, from steps, palms, heartbeats. We said they were then tied to nature, to the earth, to light, to atoms. But there is also the other side of this story. Every time we redefined a unit, moved from the body to something more abstract, we in some way understood ourselves better. We learned how our vision works because we tried to figure out why the eye is fooled when comparing weights. We learned how our perception of time works because we noticed that 5 minutes of waiting feels different from 5 minutes of fun. We learned about our own place in the universe because we measured the distance to the moon and understood how small we are. Measurement is a mirror. We point it at the world and see ourselves in the reflection, our limits, our mistakes, our ability to overcome them. Maybe that is why the history of measurement is so endless. We will never finish measuring because each measurement opens a new horizon, a new boundary, behind which lies another hidden error leading to another breakthrough. It is not a closed loop and not a straight line. It is a spiral. We return to the same questions: how much, how far, how heavy, how long, but each time at a new level. 17,000 years ago, a person painted a dot on a cave wall, one of the first attempts to record how much time had passed. Today, atomic clocks count billions of vibrations per second, and laser pulses fly to the moon and back. The spiral continues, each turn a bit more precise, a bit deeper, a bit closer to what is actually there. But at the center of the spiral is the same question, the one asked by the first person who looked at the sky and tried to count the stars. How much? The answer will never be final, and maybe in that lies the beauty. Your breathing is steady, your heart is beating. The atoms in your body are the same atoms that were born in the cores of stars billions of years ago. The hydrogen in you appeared in the first minutes after the Big Bang. The carbon and oxygen were forged in the furnaces of supernovae. You are made of star stuff, and that stuff vibrates at the same frequencies we use to define the second. You are part of the system of measurement, not because you measure anything, but because you are made of the same material, the same atoms, the same vibrations to which our units are anchored. You are not outside the system, looking in. You are inside. You are the measure. Everything is all right. The world has been measured. The world is being measured. Somewhere atomic clocks are ticking. Somewhere light is flying back from a mirror on the moon. Somewhere in a Parisian vault, behind 3 layers of glass, an old platinum cylinder lies quietly. The one that used to be the kilogram, and is now just a beautiful object with a beautiful story. You do not need to think about any of it. You do not need to count anything, measure anything, check anything. It all works. Everything is in its place. Just breathe and fall asleep.